Hey genius, welcome back to the sixth lecture of the series Periodic Table and Periodic Trends. In the previous lecture, we have learned about drawing of periodic table, trick to find out period and group of a given atomic number. We have also discussed the concept between isotope, isotone and isobar. We have learned filling of electrons, orbit and orbital concept. Now above principle of filling of electrons, and also I have shown you a trick how you can easily remember that. Apart from that, we have learned nomenclature of super heavy elements, trivial name of different elements, lanthanide and actinide construction, Slaughter's rule, determination of Sealing constant, and at the end we have discussed briefly about Goldsmith's geochemical and cosmochemical classification of elements based on chemical affinity. So these many things were discussed in lecture 5. If you have not seen that lecture 5, I will strongly recommend you please go and watch that video. And after that you can come back to this video. Now this lecture 6 is going to be a longer video because in this video I am going to discuss in detail about all the periodic trends. So just let me take the laser pointer. So in this video, we will discuss about the periodic trends in atomic radius, atomic volume, ionization energy, electron affinity, electronegativity, metallic character, and cohesive energy. And after discussing these things, each and every periodic property, I will give you some notes or some tricks to remember these periodic properties. In the right hand side, you can see for each property I have designed or I have designated an arrow. So this arrow tells that at which side this property is increasing. So this one is down left. This arrow is in the down left corner. So this trend, the atomic radius is increasing in the down left side. Whereas this one is curve shaped. You can see this atomic volume and cohesive energy. These two are in curve shaped. This means that along a period, it sometimes increases or decreases, and then again the opposite trend. For example, it decreases and then again increases. And for cohesive energy, along the period, it first increases, then decreases. And atomic radius and this metallic character, in these two cases, these two trends, you can see down left arrow. So it increases in the down left corner of the periodic table. Whereas ionization energy, electron affinity and electronegativity, these three properties increase in the upright corner. So these three properties increases in the upright corner of the periodic table. So the elements which are in the upright side, those elements are having higher ionization energy, electron affinity and electronegativity. So these things we are going to discuss in detail today. So without wasting any time, let's start the video. First thing we have to know that what is a periodic property. So any property which is periodic in nature, that means show an increasing or decreasing trend along a group or period, is called periodic property. Now the reason of periodicity. So the periodicity is the result of similar outer electronic configuration or valence shell configuration in atoms. So we can see, if we see the periodic table, we can see the atoms which are in the same group, they have similar number of valence electrons, whereas the atoms which are in the same period, they have similar number of orbits or similar number of shells. So those things matters, and those generate these periodic properties. Now, use of periodic property. So we can predict the nature of chemical bonds formed by the elements and compare their reactivity. Molecular shapes and crystal structures can also be predicted from these periodic properties. So the first property that we are going to learn about is the periodic trend of atomic radius. So this we will call it as down left property or DL property. Now let's see the model of an atom. So in the right hand side you can see this is the basic structure of an atom. So in the central core we have proton and neutrons. Together we call it nucleus. So in nucleus we have positively charged proton and neutral neutrons. So these two subatomic particles, they lie in the central. So this nucleus is actually positively charged, and surrounding that these electrons rotate in their shells or orbits. So these electrons are actually tiny particles or tiny subatomic particles. Those are negatively charged. So in a neutral atom, if we have 5 protons, we will exactly have 5 electrons. For example, if we have, for example, in sodium, we have 11 protons and we have 11 electrons. So in a neutral atom, you have same number of proton and same number of electrons. Now in the first shell, only 2 electrons can be there, and in the next 2 shells, there can be 8, at max 8 electrons. And the way of putting electrons, that first you have to fill the inner circles, only then you can fill the outer circles. So one by one you have to put in the inner circles. So first electron will come here, second electron will also come in the first orbit, next third electron will come to the second orbit, and you have to fill 8, total 8 electrons in the second orbit. Then the next one electron will come in the third orbit. So these things I have discussed in detail in the previous lecture, lecture 5. So you can go and check that lecture. Now here let's take an analogy. So here we have positively charged nucleus and negatively charged electrons are rotating surrounding this nucleus. So these two are oppositely charged. This one is positively charged and electrons are negatively charged. So there is an electrostatic attraction between these nucleus and electrons. So take it as that this core, this positively charged is actually an attractive girl. The more number of protons it has, the girl is more attractive. Okay, and take these electrons as that girl's lovers. You know, one beautiful girl has many lovers, many boy wants to get that girl's number, right? So similarly, just consider this nucleus is an attractive girl and these electrons all are her lover. Now this girl will obviously attract these boys, all these boys. The boys who are closer, these boys will get more attraction compared to the boys who are far apart, right? So because these boys are feeling some attraction, so they will try to come close. So these orbits, some special cases, these orbits, they get more compressed. For example, see, this will feel some attraction toward this side. Again, this electron, this lover will also feel attraction towards the nucleus, right? Now here all the electrons will have similar type of attraction. Whatever attraction this electron feel, the electrons which are at the same orbital, they will feel the same type of attraction. Now these things you can determine from the effective nuclear charge, which I have shown you to calculate in the previous video, how to calculate the screening constant, shielding effect or screening constant, and how to determine the Z effective. So based upon that, you can understand that how much attraction is there for each of these electrons. Now as these electrons are trying to come close to this attractive girl, so what happened, this orbit, this will actually this will shrink and this will come like this. This will become little smaller. And this shrinkage is much more prominent in case of F block elements. D block elements also shrink a little, but in case of F block elements, this shrinkage is more prominent because F electrons are diffuse in nature. So the F electrons cannot do the shielding, and the outermost electrons, they get more attraction towards this nucleus, and those electrons shrink, the shell shrink. Now as this radius shrinks, as this orbit shrinks, the radius, atomic radius also shrinks. Now how to determine the atomic radius? So atomic radius is the distance from the center of the nucleus to the outermost electron. So see, from here we have, this is the center, let's assume this is the center of the nucleus. So originally the atomic radius was from here to here, this distance, right? But as the electrons are feeling some attraction towards the center, so the orbit will shrink. The last orbit is shrinking. So now the actual atomic radius is actually this much. So the atomic radius has also shrinked. So if you increase the number of protons, the electrostatic attraction increases. So the outermost shells may contract, they may shrink, and the atomic radius can also decrease. So this is the way how the atomic radius decreases. Now, if you add one more shell, if you add fourth shell, so the fourth shell will come this way. So if you add more and more shell, that time the atomic radius of the atom will increase compared to the atoms which have lesser number of shells. Okay. So these things we are going to observe in the later slides. Let's take a look at this image. So this periodic table shows what is the relative atomic size of the atoms in the periodic table. So you can see the left hand side we have alkali metals. Those are bigger in size, and as we go in the right hand side we can see very small spheres or circles. So these are very small in size. Noble gases and halogens, those are very small in size. So what is the trend? We will see that how it is happening, what are the reasons behind it, why this size is shrinking from left to right. You can see from left to right the size is shrinking, and whenever we are going to discuss a periodic property, we will go from left to right along a period, or we will go from top to bottom along a group. Now you can see from top to bottom the size is increasing, and left to right the size is decreasing. So this is the 3D diagram which shows the atomic radius data of all the elements in a periodic table. Now let's see the trend. We will see it first for a long period. So what are the factors that are working along period? So if we go from left to right, what are the factors there? The principal quantum number is fixed. So along period, the principal quantum number is same for lithium, beryllium, boron, carbon, nitrogen. All are having the outermost electron shell as to be the second shell or second orbit. Okay. So all these atoms have two shells or two orbits. These atoms have three orbits. These atoms have four orbit. So all these atoms in the period, they have same principal quantum number. Next is the effective nuclear charge increases. So let's see this third period. Okay, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. So as we are going from left to right, we can see more and more protons are there in the nucleus. In case of sodium, there are 11 protons. In case of magnesium, there are 12 protons in the nucleus. Whereas in case of aluminum, there are 13. In case of silicon, there are 14. So the last shell is same, but in the nucleus we have more and more protons. So what I said, that nucleus is an attractive girl, right? So if it has more and more proton, so it is more and more beautiful, more attractive. So it will attract the electrons more. So I will try to show it here again. So if this is your nucleus, if you have more and more protons, it will attract more to the outermost electrons. So it will similarly attract all the electrons, even the inner electrons, but the outermost electrons, that will also shrink. So these electrons will come close. These electrons will feel more and more attraction if the proton number increases. So this shell will actually shrink. So the outermost shell will shrink, and the radius, which tells the distance from the center of the nucleus to the outermost shell, so the radius of the atom will decrease. Okay, and another factor is that when we are going from left to right, so the number of proton is increasing, similarly the number of electrons are also increasing. So we have more and more electrons in the shells, right, in the last outermost shell. So that actually increases electron repulsion, because electrons are negatively charged, and we know similar charged particle, they repel each other. So that is also a factor, but this factor is not dominant. The other factors are actually dominant. The increase of effective nuclear charge, that is the dominant factor. So as you go from left to right in a period, the effective nuclear charge increases. So although the electron repulsion increases, but that is a minor factor, because the effective nuclear charge increases. The electrons, the lovers, they feel more attraction to the attractive girl, and the shells come down. That shrinks, because of which we see the atomic radius decreases. So along period, the atomic radius decreases. Got it? Now next see the periodic trend of atomic radius along group. So along group means we are going from top to bottom this way. So what are the factors there? So along group, principal quantum number increases, means the shell number increases. So in the first one, we have this nucleus and only one shell in this one, whereas in this one we have nucleus, one cell like this, and we have one more shell on top of this. So I'm just doing half circles because I'm not showing the entire circle. Just consider this as an entire circle. Okay, now in case of third period, we have three shells. Similarly, in case of fourth period, we have four shells, then here five shells, six shells. So as we go from top to down, the principal quantum number increases, means the number of shell increases. Now effective nuclear charge also increases little bit, but that that is a minor factor. So the red ones, I have written the minor factors in the red ones, so these don't contribute much. So even if we see that we have seen along period that electron repulsion was also a factor, but that was also minor factor, so that's why I wrote it in red. Here also effective nuclear charge increases, but this is a minor factor, so that's why we will ignore it. We will ignore the contribution of this. This I have written just to give you the complete information that what are the factors working. So the black ones are the dominant, and these red ones are minor factors, so we can ignore them. But to teach you, for learning purpose, you have to learn everything. Now the other factor is the size increases because we have more and more shells, right? But the increasing rate of size for the heavier containers decreases. Yeah, so the size will continuously increase when we have more and more shell, but the rate of the increase will decrease. Maybe just see here, from 37 it became 152 uh, as in pm, means picometer. Now after that it is 186, 227. Now if you see from 227 to 248, the increase is very less, and again 248 to 265, the increase there is increase, but the rate of increase is much lesser. So if we subtract this, we can see there is almost 115 picometer change. Now in between lithium and sodium, if we see, that is 34, the change in picometer. I'm just telling you the change in the size. Now sodium to potassium, so that will be here 14, here 27, means 41. Now from potassium to rubidium, you can see the change is only of 21 picometer. Now from rubidium to cesium, the change is just 17 picometer. So you can see, as we go in the heavier atoms, the rate of increase, it is increasing, the atomic radius is increasing, but the rate of increase decreases. The rate of change is significantly less in d block elements due to the less shielding of d and f electrons. Yeah, so another factor is, when you consider the d block elements, as I told that in the previous lecture, that d electrons and f electrons, they are more diffuse in nature, they have lesser shielding property, so the nucleus attracts the electron much more. Now if you input more and more protons, more and more electrons, still the attraction remains almost same, and because of that, the rate of change in the side by side elements, that is small. That I will show you. I'll show you in the periodic table. I'll show you here. You see these d block elements. If you see these d block elements, see, if you go from top to bottom, the change of the size is less, not very significant. Whereas if you go in the s block elements, you see a huge change, huge increase in the atomic radius. Whereas in case of d block elements, the change is slow. So along the group, the atomic radius increases. Okay, what is the major factor? Major factor is that the principal quantum number is increasing as we have more, as we are going from top to down, the more and more shells are adding. So that's why the atomic radius is increasing. Now this is the chart which tells you Z versus R, means atomic number versus that radius of atom or radius of orbital. Now you can see for the uh, so these are the s block elements. For s block elements, the atomic radius is more for the alkali metals, and as we go along the period from lithium to beryllium, boron, carbon, nitrogen, oxygen, so the atomic radius decreases. So it decreases till neon. So neon, which is the inert gas element, that is having lowest one here, and again in the next electron, when we fill the next electron, that goes in the third shell, right? Third orbit. So that's why again the size increases. Here you can see sodium. So again if you put more and more proton and electrons, the size decreases till the next uh, inert gas element, argon. And again if you put one more electron and proton, that size again increases in the potassium. So just see this graph and try to understand. So this is the values that I have found, that atomic radius values. If you need, you can take a note of this. Now the values which are given without bracket, so that tells the single bond covalent radius, single bonded covalent radius. And within the bracket, so these values which are inside the bracket, so that gives atomic or metallic radius. So in the atomic state, so these values are in the atomic state, whereas these values which are non-bond without any parenthesis, without any bracket, so that gives a covalent radius. And yeah, these values are given in uh, picometer. So picometer is actually 10 to the power minus 12 meter. So 1 picometer is 10 to the power minus 12 meter. So our hair is in the order of micrometer, 10 to the power minus 6 meter. Now if you divide this 10 to the power 6 times, that will be a picometer. Then you can understand how much tiny that value is, how much smaller the value of an atom or radius of an atom is. Now we will discuss about some concepts regarding atomic radius and ionic radius. So cations having lesser number of electrons experiences higher electrostatic attraction, giving lesser radius compared to its elemental form. So let's see, we have these elements here in the elemental form: lithium, sodium, potassium, beryllium, magnesium, calcium, and in this side we have fluorine, chlorine, bromine, iodine. Now these atoms, here we have similar number of protons and same number of electrons. So number of proton and electrons are same. But when we take out an electron, in that case number of proton is more and number of electron is less. So that time we get cations. These are the cations. And when we put an extra electron in this elemental form, so that time we have lesser number of protons and we have more number of electrons. So that time we get anions. So these right hand side ones are the anions. Now it is saying that cations having lesser number of electrons, because we have already removed one or more electron, right? So in this case we have removed one electrons from lithium, sodium and potassium. So it has now less number of electron, one less electron. In sodium we had 11 protons and 11 neutrons, sorry, 11 protons and 11 electrons. Now we have removed one, so now we have 11 protons and 10 electrons. So we have less number of electrons, and that experiences higher electrostatic attraction, because now we are removing one electron, so one lover is removed. So now the nucleus or the attractive girl, that can give more love to each electrons, right? So that can give more time or more attraction. So that's why the electrons feel more attraction now. Just I will try to clear this concept here. See, this is my nucleus and these are the shells. Let's see in case of sodium. In case of sodium, we have 2 electrons here in the first shell. Then we have 8 electrons in the next shell, and we have 1 electron in the last shell. So this one is in the last shell, right? Now what happens when we remove this electron? If we just remove this electron, we take it out, so sodium becomes sodium plus, and in that case this orbit is completely empty. This third orbit, it had only 1 electron, right now it is 0. So you can see only these two orbits are there now in Na plus, sodium plus. So obviously the number of orbit is less. And even if you take magnesium, so in magnesium there were 2 electrons, and if we remove 1 electron, that time we will have a total 12 proton, 12 number of proton, and 11 electrons in case of magnesium plus. But when we do magnesium 2 plus, that time we are removing both the electrons. This is also we are removing. So whenever we are removing both the electrons in case of magnesium, again this third shell is becoming vacant, 0. So that time we have 12 protons and 10 electrons. So we can see the number of proton is more, number of electron is less. So the attraction towards the nucleus for each electron will increase, and that decreases the size. So that's why cations are always in smaller size compared to their elements. You can see in case of lithium, the size is more compared to lithium plus. The sodium size is more compared to the sodium plus. Potassium size is more compared to potassium plus. And these are in given 10 to the minus 10 meter. Okay. So if you want to convert it into picometer, just multiply by 100. So this is 203 picometer, and this is now 138 picometer. Similarly, in case of beryllium, we had 96 picometer size, but beryllium 2 plus is only 45 picometer. Magnesium 1.45 picometer and Mg2 plus is only 0.72 picometer. But in case of anions, let's see the case of anions. Anions having higher number of electrons experiences higher electrostatic repulsion. See, in case of anions, in case of fluorine, if you take fluorine, so we had this, I will draw here. This is the nucleus, this is the first shell, and this is the second shell. So in the first shell we had 2 electrons, and in the second shell we had 7 electrons in case of fluorine. But when we are putting 1 electron, so we are putting one more electron here to here in the orbit. So we are doing 7 plus 1. So 1 electron is increasing. Now we have 2 electrons in the first orbit and 8 electrons in the next orbit. So in case of fluorine minus, we have total 9 protons but 10 electrons. So we are putting one extra electron. That electron, so we already had several electrons. We already had 7 electrons, and then we are putting one more electron. So what will happen if we increase more number of students? There will be more chaos, right? More fight, more quarrel. So when we are adding one more electron, that time the electron-electron repulsion increases. And because of that electron-electron repulsion, these electrons will try to go away from each other. This will try to go this side, this will try to go this side. So that will actually expand this orbit size. So because of this, the size of fluorine is smaller, but the size of fluoride ion is actually much bigger, because these electrons are trying to go away from each other. So as we are putting extra electron, the electron-electron repulsion is increasing. Those electrons are trying to go away from each other, and because of that, the shell is expanding. and we are getting higher value of radius, ionic radius or anionic radius, compared to the elemental form. You can see even in case of bromine, in the elemental form it was 120 picometer, but in the bromide form it is 196 picometer. And you can see the expand of iodine as well, from 139 picometer to 220 picometer. So we have understood that in case of cations, because we are removing electrons, so either the shell number of shell is decreasing or the electrostatic interaction is increasing. So both factors are reducing the size of the cations. It may happen that the shell is in decreasing, means earlier it was 3 shells, now in case of sodium plus there are only 2 shells. Similarly in case of magnesium it had 3 shells, but in case of Mg2 plus there are only 2 shells. Or even the shell number is same, but still if you remove electron, that will increase the electrostatic interaction. So because of that, the size of the cation is always smaller than the elemental form. And as we are putting extra electron, so that will increase the electron-electron repulsion. So because of that, the orbital or orbit will try to expand, and for that reason the size of anions are every time bigger than the elemental size or elemental radius, right? Next point is similar charge species along a group follows the same periodic trend as of the corresponding atoms. So the ionic radius trend follows exactly the same as the atomic radius trend. For example, we see in case of lithium, sodium and potassium, if we go from top to bottom, we can see the size is increasing, the atomic radius is increasing. Similarly, if we consider lithium plus, sodium plus and potassium plus, we can see here also the size is gradually increasing from lithium to potassium. And that is the thing, this ionic species, if it has same number of charge, that will every time follow the same periodic trend as of the elemental forms. So even if you take electron or give electron, if you convert in the ions and if you convert in the same nature of ion, if it is 1 plus, you have to compare it with 1 plus charge. If it is 2 plus, you have to compare this with the 2 plus charge. So if you do so, you will have the same periodic trend as of the atomic radius trend. But yes, you cannot compare the lithium plus to fluorine minus, F minus, fluoride. These are not same charges. You can see here it is plus 1, here it is plus 1 and here it is minus 1. So you cannot compare those to take the periodic trend, or you cannot compare this plus 1 to plus 2. So these are not similar charge. If you have similar charge species, only then this rule will apply and the ionic radius trend will exactly follow the atomic radius trend. Fine. So what we have learned in this segment. So from this segment, we have seen that the trend of atomic radius is actually a DL property, down left property. So it increases in the down and left side. And the size or radius of an atom decreases from the left to right of a period. We have also learned that size or radius of an atom increases from top to down of a group. So what we have observed, that from here to here, from left to right, it decreases, right? So we can see from right to left, it actually increases. And we have also seen that from top to bottom, it increases. So from top to bottom, it is increasing, and from right to left, it is increasing. So that's why we can see that this is the arrow which tells in which side the atomic radius is increasing. So that's why if you go back to my first slide, you can see that I have given a small arrow on the side, on the right hand side of periodic trend of atomic radius. Next point is that alkali metal ions are having highest atomic or ionic radius and inert gases are having lowest atomic radius in a same period. The variation in ionic radius for a particular oxidation state follows the same trend as of the atomic trend. And additional information is that radial distribution function of the electrons in the outermost shell is required to calculate the atomic radius. So we calculate this atomic radius from the RDF function. So it is theoretically calculated in a free atomic state as the distance from the nucleus to the point at which the radial distribution probability of the outermost orbital electrons is maximum. So theoretically we calculate in a free atomic state this atomic radius which is from the center of the nucleus to the outermost electron orbital, or where the this radial distribution probability function is maximum. Next we are going to discuss about the periodic trend of atomic volume. So this we will remember as a curvy property. Now why curvy, that I will discuss. So let's see the 3D diagram. You can see the atomic volume is higher in this side, and as we going from left to right it is actually flat or zero, and again if we go more right it is again increasing. So the atomic volume, eh, first it is decreasing, then it is almost similar in this range, and then again it is increasing. Now let's see the definition of atomic volume. So the volume occupied by 1 gram of atom of the element in solid state is called the atomic volume. So Lothar Meyer is remembered for atomic volume curve. He made a graph taking 28 elements. So that time very less number of elements were known. Later which was modified and all other elements are also plotted. So the definition of atomic volume is simply the definition of volume, right? Atomic volume is atomic weight divided by its density. Now, this atomic volume depends on multiple factors. For example, packing efficiency and crystal structure, allotropic forms, temperature. So all these things actually can influence the atomic volume. Now let's see the atomic volume along period. So first we will see it for S and P block elements. This is just for S and P block elements we are observing now. So what happens? Along period, if we go from left to right, the principal quantum number is fixed because in the same period we have same number of cells in all the elements, right? So the principal quantum number is fixed even if we go from left to right. Now at beginning, increased effective nuclear charge predominates. So what was happening in the beginning when we go from, let's take this, from lithium to beryllium to boron. So when we go from left to right, the effective nuclear charge is also increasing because we are putting more number of protons, right? So at the first, the effective nuclear charge predominates. So the electropositive elements of the period lies in the descending limb, lower atomic value. So that's why when we are um, increasing the number of protons from lithium to beryllium to boron, then we can see the effective nuclear charge is more. Because of that, the nucleus is attracting the electrons. I'll draw it again. So as we putting more and more protons, the girl is becoming more and more attractive. So these lovers, they will try to come close, right? So these faraway lovers or the electrons, they will try to come close and the orbit will shrink. So that's why the volume or space which it is occupying, that is also decreasing. And in case of electropositive elements, so as more and more proton we are putting, the volume is decreasing, again decreasing, again decreasing, again decreasing. Okay, that's why the electropositive elements lie in the descending limb. So these limbs in this graph, these limbs are called the descending limbs. You can see here, these are the descending limbs. So it lies, the electropositive elements lies in the descending limbs. Now while filling more electrons, now electron-electron repulsion increases. So now if we put more and more electrons, first it was happening that the effective nuclear charge was increasing and the size was shrinking, right? But now if we put more and more electrons at a time, what happens? Now these electrons start to fight. Okay. Now they start to repel each other because they are same charge, negatively charged particle. So they will start fighting and they will try to go away from each other. So now this component is less and this component is more. These electron will try to go away from each other. So because of that, the orbital size will increase, or you can say uh, this electron-electron repulsion will increase. So the electronegative elements lies in the ascending segment of the curve. So you can see these electronegative segment elements, they are lying in the ascending curves. Here. Now first the effective nuclear charge was dominating, and next is that electron-electron repulsion will dominate. So although size will not increase as much, but actually the atomic volume will start increasing. So this is true for S and P block element. Now next see what happens in case of D block elements. So we are now observing a long period for D block elements. So for D block elements, at first atomic volume decreases due to increasing effective nuclear charge. So the same thing, as we increasing the number of protons and electrons from scandium to titanium to vanadium and chromium, we can see the number of proton is increasing. So the electrostatic attraction is increasing, and that's why the size is shrinking and the atomic volume decreases. So then electron-electron repulsion balances the effect of increasing effective nuclear charge. So more or less atomic volume remains constant. So now if you put more and more protons and electrons, if you go from iron to cobalt, nickel, so that time the electrostatic attraction is also increasing. At the same time, electron-electron repulsion is also increasing. So both the factors are actually balancing each other. Means if you see it again, so because of the electrostatic attraction, if it wants to come this side, so because of the electron-electron repulsion, it wants to go in the outer side. And those two magnitudes are almost same. So they actually cancels each other. The effect cancels each other. And at the last, electron-electron repulsion predominates and atomic volume increases for copper and zinc. Sorry, this will be zinc. So at the end of the D block elements, you put more and more electrons and protons. So that time this electron-electron repulsion predominates and the atomic volume increases. So this is the crude way to remember these things. But the main definition is that atomic volume is actually atomic weight divided by density. This thing. So both the factors actually contribute. Now let's see along the group. So what are the factors that are working along the group? So along the group, atomic weight increases Yeah, so we are putting more and more protons and neutrons in the nucleus, so the atomic weight increases. Now atomic density also increases, which works in the opposite direction. Yeah, so these red ones, I have written the red ones, which are working in the opposite direction, or which are the minor factors, which this is not dominant. The black ones are the dominant factors. Okay, now we have seen that atomic volume is equals to atomic weight divided by density. Now atomic weight is increasing as well as density is also increasing, but the increase of atomic weight is the dominant, that is more. So hence the atomic volume increases along group. So if we see along group, we can see the atomic volume will increase because of the increase in atomic weight. Okay, now you can see from here also, see this lithium, then in the group we will have sodium, we will have potassium and rubidium. So these are in a group, and we can see the atomic volume amount is actually increasing. This is a set versus atomic volume curve. So you can see if we increase the atomic number or number of protons, how this behaves. So I will take this one. Yeah, just take this potassium, calcium. So when we increase the number of protons, the electrostatic interaction is increasing. So the atomic volume is going down. Same thing is in the D block elements also, scandium, titanium, vanadium. When we increase more and more proton, the atomic um, electrostatic interaction increases and the atomic volume decreases. Now after that, in case of this iron, cobalt, nickel, we can see this zone. So this zone, in this case, we are putting more and more electrons and protons. So as we are increasing the protons, the atomic attraction or electrostatic attraction is increasing. But at the same time, as we are putting electrons also, the electrostatic repulsion also increases between the electrons of the same shell. So both the factors balances out each other, and that's why we have almost same kind of atomic volume. Now when we put more and more protons and electrons, so that time the electron repulsion that increases, and because of that we get increase in the atomic volume. Same thing happened in the p block elements also. As we put more and more electrons, the atomic volume will increase because of the electron repulsion. Fine. So till now, what we have seen? We have seen that atomic volume is actually a curvy property. So it first decreases and then increases. So along a period, atomic volume first decreases due to the increasing effect. Just let me take this laser pointer. Yeah. So along a period, atomic volume first decreases due to the increasing effective nuclear charge. Then the electron repulsion starts to increase and atomic volume also increases. Along a group, atomic volume increases due to the increase in atomic weight. Alkali metal ions having highest atomic volume occupies the peaks of the graph. So if you see this graph, so the peaks are occupied by the alkali metal ions here. All these are alkali metal ions which are occupying the peaks. With the increase of atomic number, the electropositive elements lie on the descending limb, whereas the electronegative elements lie on the ascending limbs. For the transition metals, the atomic volume remains almost same along the period, and they occupy the flat region at the bottom. Whereas in the case of lanthanides and actinides, they occupy the descending limbs near the bottom because of the lanthanide and actinide contraction. So this lanthanide and actinide contraction I have explained in the previous lecture. So these are some keynotes that you need to remember. for the case of atomic volume or the periodic trend of atomic volume. Now let's discuss about the periodic trend of ionization energy. So this is a upright property. So I call it upright property. Now I will explain why it is called upright property. Just let me take the pen. Yeah, so first thing we have to understand that what is the concept of ionization energy. Now let's try to see this thing. You see, this is a kid who is holding a lot of balloons. Now what you can do, you can cut a wire, a rope, right? If you cut a rope, what will happen? One of the balloon will fly, right? Similarly, you can cut another rope, and similarly another balloon will fly, and those balloons will go out of his hand, out of his control. Okay, so what kind of energy you are providing? You are cutting the rope, and that's why these balloons can get free. Those are getting free and out of this boy's control. So similar concept you have to visualize in case of atom. In case of atom, you see, they have electrons in the shells. What you can do, you can knock out this electron. You can provide some energy so that this electron will go away, and that will go out of control of this atom. So as this electron is going away, so this electron is minus charge, negatively charged. So this atom will become positively charged. So let's see the definition now. So the amount of energy required to knock out the loosely bound electron in the outermost shell in an isolated atom in the gaseous phase to generate a charged cation is referred as the ionization energy of the element. I know this looks a big definition, but let's try to understand it by small portions. So the amount of energy required, so the amount of energy that we are supplying to cut these balloons, okay? So that work, that amount of energy, that is referring to the ionization energy. To knock out the loosely bound electron. So we can knock out the outermost electrons or the electrons which are not tightly bound, which are loosely bound, so that we can easily knock them out, right? We can provide some energy and it will go out. In the outermost shell, as I already mentioned, that we will knock out the electrons from the outermost shell in an isolated atom. So this one is very important in case of the definition of ionization energy. It has to consider the isolated atom. So this atom cannot be with the other atoms, or it cannot be bonded with another atom. It cannot be bonded with B, or it cannot stay with the other A type of atoms. If it stays with other atoms, na, so there will be some interaction. So that interaction energy also you have to keep in mind. You have to calculate. So you have to calculate more things if it is in surroundings of other atoms. So what you have to do, first you have to provide some energy, and you have to take out this atom in seclusion. This has to be an isolated atom. No one should be in its surroundings. Only then this ionization energy definition you can apply. And in the gaseous phase, so you have to take it, this ion or atom, to the gaseous phase to generate a charged cation. So as you are taking electrons from here, you can see if you are taking electron from here, so you will generate a cation, and that is referred as the ionization energy of element. So the energy you are providing, so the energy you are providing to take electrons from the outermost shell of an isolated atom, that much energy is called ionization energy. Now we will see these definitions or some examples. In case of this, see, aluminium. So aluminium has 13 electrons. Now what will be the arrangement? I'll do it here. Just assume this one is the nucleus of aluminum. Then we have 2 electrons in the first shell, 8 electrons in the second shell, and 3 electrons in the third shell. So 2, 8, and 3. So in our outermost shell, we have 3 electrons. And all these 3 electrons we can take one by one. So what are we doing? First, we are taking 1 electron, and the ionization energy is this 578 kilojoule per mole. Now, when we are taking 1 electron, so we are doing 3 minus 1. So in the last shell, now we have 2 electrons. So if there are less number of electrons and more number of protons, we know in case of cations, the electrostatic interaction will be more, and those outermost electrons will be now tightly bound. They will feel more attraction towards the attractive girl or the nucleus, right? So now when we are trying to take out another electron from this aluminum plus, from this, if we want to take out another electron, so we have to supply more energy. That's why this IE2 is actually greater than this IE1, ionization energy 1. Now we have taken out another electron, supplying more energy. So now we have, now we have only 1 electrons in the third shell or outermost shell. So in total now we have 13 protons and only 11 electrons. So now we have lesser number of electrons and much more lesser. So the attraction energy of the nucleus will be more and more. So when we try to take out another electron from aluminum 2 plus to generate aluminum 3 plus, we actually have to provide much more energy. And you can see this much energy we have to provide, 2744.8 kilojoule per mole, which is actually more than the summation of its IE1 and IE2. Even if you sum these two, this number is much greater. So you can take out electrons from an atom one by one, but as the number of electrons are decreasing and the number of protons are increasing in the ion, so they will experience more and more attraction. So you have to provide more and more energy to take out the outermost electrons. Okay, clear? Now let's see the periodic trend. So you can see I have already mentioned it. This is a upright property. So if you see the periodic table, the ionization energy increases from left to right in a period, and uh, if you go from top to bottom, the ionization energy actually decreases. So we can say that ionization energy increases from bottom to top. So if you go from bottom to top, the ionization energy increases. So actually we can say that this is increasing in this upright corner of this periodic table, right? So that's why I tell it as UR property or upright property. Now let's see this 3D periodic table of ionization energy for your easier visualization. Now you can see from left to right, the ionization energy is increasing. Even if you consider this part only p block element, let's see from left to right, the ionization energy is increasing. And from top to bottom, the ionization energy is decreasing. So actually from bottom to top, the ionization energy is increasing. So this corner is having the most ionization energy. So this graph is based on the first ionization energy. Okay. Now let's see the detail of the periodic trend. First, we will see along period. What are the factors that are working along period? So along period, principal quantum number is fixed. So the number of shell is fixed. So if you go from boron to carbon to nitrogen, oxygen, the principal quantum number or the number of shell is fixed, or the number of orbit is fixed. Effective nuclear charge increases. We have already seen as we go from left to right, we are putting more and more protons in the nucleus. So the girl is more and more attractive. So that's why that girl attracts the lovers or the electrons more, right? So the effective nuclear charge increases from left to right along period. The size gradually decreases. The atomic size also is decreasing from left to right because of the increase in the effective nuclear charge, right? So all these factors actually increase the ionization energy from left to right. Now another factor, this electron-electron repulsion, that also increases from the left to right, but actually this is negligible factor in case of ionization energy. So that's why I'm writing it in red. Okay, so this factor is very minor and you have to neglect this factor. So thus, the electrostatic attraction towards the nucleus increases along the period and ionization energy goes up. Just simply try to understand, if we have a smaller atom where the electrostatic interaction is more, and if we have a bigger atom, in case of bigger atoms, the shells, just consider that we have a bigger atom and these valence electrons are also far apart. So if these valence electrons are far apart, it will not have much control. The nucleus will not have much control on the electron, right? So you can easily take out this outermost electron. But sorry, as the size is small and effective nuclear charge is more in this atom, so if you try to take out this electron, you have to put more and more energy, right? So that's why as you go from left to right along a period, the effective nuclear charge increases, size decreases. So all these factors make this electron tightly bound or tightly attracted towards nucleus. So that's why it takes higher energy to take it out in the gaseous phase. Okay, so it takes higher energy. So that's why the ionization energy is more. Yeah, so there are some exceptional cases. For example, I can show you here. Just give. So you see, just see this: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So if you see this one, so we are expecting the ionization energy will increase along the period, right? That is happening from lithium to beryllium. But for some reason from beryllium to boron, it is actually decreasing. And again, boron, carbon, nitrogen, these are increasing. The trend is fine here. But again here from nitrogen to oxygen, the ionization energy is decreasing. So there are some exceptions and we are going to talk about that. So according to general periodic trend, oxygen should have higher ionization energy compared to nitrogen. Yeah, because nitrogen is having atomic number 7, oxygen is having atomic number 8, right? So oxygen comes right to the nitrogen. So according to the periodic trend, oxygen should have higher ionization energy. But it is having lower. Why? Due to the half-filled electronic configuration, nitrogen has higher ionization energy. So I will explain it later in detail, but just in a brief, I will say this electronic configuration. See this electronic configuration. So this electronic configuration I have already taught in the previous lecture. If you have not seen, you can go and check the lecture 5. You can see it is 2p3 and this one is 2p4. Now if I draw this 2p, for nitrogen we have 2p3. So one electron here, one electron here, and one electron here. Now same thing for oxygen. So one electron here, second electron here, third electron here, and fourth electron. Note down, I have drawn three electrons, all three are in up spin. Now when I put the fourth electron, that will share with this electron, and now this cannot be the up spin. So this electron will be down spin. Due to Pauli's rule, the electrons in the same shell cannot be of the same spin. Okay. So as I am putting the fourth electron, I will put it as a down spin. Now in this case, in case of nitrogen, we have 2p3 configuration. So this is half filled. This is called half filled because we can at max put 2 electrons and 2 electrons. We can put maximum 6 electrons in this 2p orbital. But we have put only 3 electrons. So this is half filled. Whereas in case of oxygen, it is 2p4. So here 2 electrons, here 1 and here 1. So total 4 electrons. So this half fill and full fill shells, they have surprisingly high stability because they are having higher exchange energy. I will explain this exchange energy in some after some slides in the same this lecture. So because of this half fill configuration, it is having more exchange energy. So the exchange energy means this electron can go here, this electron can come here, or this electron can go here, this electron can come here. So all this kind of possible exchange can happen. So that's why this nitrogen is having higher exchange energy, and it is more stable. Because of that fact, if we try to remove one electron from this nitrogen, so this ionization energy will be much high compared to the oxygen's ionization energy. So from oxygen, if we want to simply remove one electron, we can simply remove this electron. But from nitrogen, if you want to remove electron, so that time the ionization energy will the exchange energy will decrease. So these electrons can exchange their positions, and that's why they have better stability. But if you remove one electron, so that time their exchange energy will decrease. So that's why this nitrogen will not let it go. It will not let the electron go. Okay. Because of that reason, the ionization energy of nitrogen, first ionization energy of nitrogen is more compared to the first ionization energy of the oxygen. Okay. But now consider the second ionization energy. So we have already removed one electron. So I'll just uh, erase this. Wait. So we have removed one electron. Just assume we have removed this electron from the nitrogen, and we have removed this downspin electron from the oxygen. So in this case, now we see there are only 2 electrons, and the exchange energy is also very less for nitrogen because it is not half filled. But now this O positive, that is actually half filled. There are only 3 electrons, and in this half filled configuration they have higher exchange energy. So if we consider the second ionization energy, if you want to try to if you try to remove one more electron, so that time we have to spend lesser energy in case of N plus, but we have to spend much more energy in case of O plus, because O plus got stable state, this stable half filled state. Now you are trying to disturb it, you are trying to take one electron again. So that time this O plus will not let it go. It will not let the electron go. So that's why you have to put more and more energy. Okay, got it? Let's see some more cases. For example, if you see phosphorus and sulfur, so similar to the nitrogen and oxygen case, phosphorus is having 3p3 and sulfur is having 3p4. So that's why if we consider the first ionization energy, the phosphorus will have higher first ionization energy compared to the sulfur, right? But now it is becoming phosphorus positive and sulfur positive. Now it has 3p2, only 2p electrons, and sulfur positive is having 3p electrons. So now this S plus sulfur positive is now half filled. So it is much stable. So now if we try to remove one more electron from phosphorus positive and the sulfur positive, so that time we are removing electron from this 3p2 and 3p3. So this time this second ionization energy will be lesser in case of P plus, whereas it will be higher in case of sulfur positive. But this is not universal, okay? So this works in this concept of exchange energy and gaining stability through this exchange energy, that works well in case of lighter elements. So this exchange energy concept does not have effect in the heavier elements, and they follow normal periodic trend. So if you go along the period from left to right, it will increase. The ionization energy will increase. That thing happens in case of this antimony, tellurium, bismuth, and polonium. If you see, this is having 5p3, 5p4, and bismuth and polonium, they are having 6p3 and 6p4. So from the half-filled nature, we expect this antimony will have higher ionization energy, first ionization energy, but that is not true. You can see antimony is having lower first ionization energy. Sorry for that. So antimony will have a lower first ionization energy compared to the tellurium. You see, it is having higher first ionization energy. Similarly, from the exchange rule or from the half-filled concept, we might expect that bismuth will having higher ionization energy compared to this polonium, but that is not true. So if we see, this will be actually first ionization energy, sorry. If we see the first ionization energy of this bismuth and polonium, we can see bismuth is having lower ionization energy, whereas polonium is having higher ionization energy. Now let's try to remember this trend. That how we can remember this ionization energy trend. So if you take these three periods, period 2, 3 and 4, and you will see, so these are the lighter elements or the lighter atoms. So they actually, in these lighter atoms, the concept of half field and exchange energy, that actually works well. That already we have seen in case of nitrogen and oxygen, right? For that, the ionization energy trend is like this. So it first increase, then it will decrease, then again it will increase, then again it will decrease, and again it will increase. So this is how I remember it, based on 2-3-3 formula. So first I will increase till 2 elements, means lithium and beryllium. Then I will decrease 1, I'll come to boron, and then I will take 3 more elements, means boron, carbon and nitrogen, that will increase. Then again I will come down in case of oxygen, I will come down, and then again I will increase 3, oxygen, fluorine and neon. Similarly, in case of period 3, I'm sorry, I'm using a very primitive setup. Yeah, so again in case of sodium and magnesium, so these two will increase. Then again in case of aluminum, it will decrease. And then again aluminum, silicon, phosphorus, it will increase. Again from phosphorus to sulfur, it will decrease. And again sulfur, chlorine and argon, it will increase. So I remember this trend of these three periods as a 2-3-3 formula. And these ones, these elements, for example, beryllium and nitrogen, or magnesium and phosphorus, these peak elements, they are actually full filled and half filled. So that's why they are having higher stability, higher exchange energy. If you see the electronic configuration of beryllium, it is 2:2, that is full filled. In case of nitrogen, it is 2p3, that is half filled. So these full field and half field configuration, they have higher exchange energy, and that's why they are having higher ionization energy compared to their nearby atom, right-sided atom. But as I said, that this concept of exchange energy and half field concept, that works well in the lower atomic number elements, but in case of these higher atomic number elements, that do not work. And for the next period, this will be period 5. For the period 5, you can see it will just monotonously increase. The ionization energy will increase. Similarly, in case of period 6, it will increase and then it will decrease for one, and then again it will increase. And this element is actually lead. So cesium, barium, thorium and lead, that will increase, and then in bismuth it will decrease, and then again it will increase. So when I used to prepare for competitive exams, I used to remember these trends. First 3 periods will be 2-3-3 formula, next period will be monotonously increase, and the last next period will increase till lead, then decrease, and then again increase. So as I have already mentioned, this half field and full field concept, you can see in case of boron it is 2p1, and in p electrons can p orbital can take at most 6 electrons. Now we have only one. In case of carbon we have 2 electrons, and in case of nitrogen we have 3 electrons. So 3 is actually half field. At most we can have 6 electrons, we have 3 electrons, so that is a half field configuration that is having higher exchange energy, so that's why it is more stable. So this half field and full field concept we will learn in the later slides. Yeah, so this is the filling of electrons that I have already discussed in the previous lecture. So you can see you have to learn this electronic configuration. So first electron goes in 1s, and that is 1s1 in case of hydrogen. Then the next electron, that also goes in 1s, and in case of helium we have 2 electrons, and those spins are opposite in nature. One is up spin, another one is down spin. Now the next electron goes in 2s and we get lithium. The next electron goes in again 2s and we get 1s2 2s2, that gives beryllium. So here 1s2, 2 electrons are oppositely spinned. Here also both the electrons have opposite spin. Now the next electron goes in 2p, and if we put one more electron, that will go here, another 2p, and if we put one more electron, that will also go in another 2p. And after that, if we put one more electron, that means 2p4 in case of oxygen, that electron will go here and that will have down spin. In case of fluorine, we will have one more electron, and in case of neon we will have full filled configuration. So this is the electronic configuration you can see. And if we put one more electrons after this 2p, that will go in 3s. The next electron will also go in 3s, it will pair up. And if we put one more electron, that will go in 3p in case of aluminium, and then we put one more electron in silicon, phosphorus. So this 3p3, this will be again half filled configuration. Now we put more and more electrons, and in case of argon we get again full filled configuration. So this is how you can put electrons and you can determine the electronic configurations. So now we are going to understand the concept of exchange energy. So in case of lithium, we have 1s2 and 2s1, only one electron. In case of beryllium, we have 1s2, 2s2. Now this beryllium in 2s, now it has 2 electrons. So this is actually full filled. Now these electrons, or these full filled electrons, are actually called they are having higher stability. Now I will explain it in case of nitrogen and oxygen. Let's see again. In case of boron, we have 1s2, 2s2 and 2p1. In case of carbon, we have 1s2, 2s2 and 2p2. So the next electron will go here. Now we will do the nitrogen. We have 1s2, 2s2 and 2p3. In case of nitrogen, we have 1s2, 2s2, 2p3. Now this 2p3, so all the px, py and pz orbitals, they are having 1 electrons. This is actually half filled configuration. So these electrons which are half filled can now actually change their position. What I will do, I will just draw it like this. So this is the crude idea which I am telling you to understand this exchange energy. Now in the 2p we have 3 electrons, right? So let's write it as 1, 2 and 3. Let's consider it as 1. This one is as 2, electron 2 and electron 3. So this can be in this order, or this can be like this: 2, 3, 1, or this 2 and 3 can exchange their positions, right? So it can be 3, 2, 1. So all these possibilities can happen. So these electrons can change their place. The thing is, these electrons are occupying the shells. That's why they can change their place. If it is a vacant shell, you should not calculate it. I mean, you should not consider it that this electron will go here in this position. Okay. So if in this case, in case of carbon, these 2 electrons can change their positions. Similarly, in case of nitrogen, all the 3 electrons can change their position. Now this gives higher exchange energy. That is called exchange energy. That electron can go from here to here, and this electron can go from here to here. So this is more in case of half filled configuration. But when we have 2p4, p1, p2, p3 and p4. Now you might say that still these 3 electrons can change their position, but actually not, because these are paired electrons. These electrons have their interactions, and though these 2 electrons can change their position, but the exchange energy actually decreases from the compared to the nitrogen. Now that exchange energy will increase again in case of neon. If you see the electronic configuration of neon, so that will be actually 2p1, 2p2, 2p3, then 2p4, 2p5 and 2p6. Now these 3 electrons which are having up spin, they can change their position, they can have exchange energy, and these 3 electrons which have down spin, they can change their position and they can have exchange energy. So this configuration, full filled configuration, is actually having 2 times of exchange energy compared to this nitrogen, right? So this is having 2 times of exchange energy. But there is another thing, that we have to consider is the pairing energy. So as the electrons are paired here, so we have to subtract some term which is called pairing energy. For example, if we write exchange energy like E, so for 3 electrons we have E3 exchange energy. Okay, now here it will be E3. This 3 electrons generates E3, the upspin 3 electrons, and another E3 for the downspin 3 electrons. So let's try to understand again. Here we have 3 upspin electrons that can change their position, and that will gain this E3 term, E3 energy, stability. And these electrons, these 3 electrons which are having lower spin, they can also exchange their positions, and that will have another E3 exchange energy. Apart from this, we have some pairing energy also, that actually we have to subtract, because there are 3 pairs. When we are trying to exchange these electrons, we are breaking that pair. So if we take out these electrons, I will take the laser pointer for this. Yeah, see, so this is a pair, right? And this is another pair, this one is another pair. So these electrons are close to each other, they have some kind of interaction, they have some kind of uh, energy going on, energy exchange going on in between them. So when I'm trying to do exchange of this downspin electron with this downspin electron, so I'm trying to change the position of these two. So that time first I'm breaking this pair, then I'm breaking this pair, and then I'm changing the position, I'm making new pairs. So to break that pair, to break those previous paired electrons, we need to give some pairing energy. So that actually decreases the stability. So now here we have 3 pairs. So crudely we can say 3p. So these electrons are changing, exchanging the upspin electrons. That's why we are getting stability in terms of exchange energy, E3. These electrons, downspin electrons, are also exchanging in between them. That's why we are getting another stabilizing energy term, another E3. And we are breaking these pairs. So that's why we have to uh, apply some energy. We have to expend some energy. So that's why this 3 pairing energy we have to subtract. So now this one is the stabilizing energy that is working for this full field configuration. In the half field configuration, it was only E3. There were no pairing. We were not breaking any pair, right? But in case of full field, we have paired electrons, and to exchange the electrons into the same spin electrons, so we have to give some pairing energy to break those pairs. So actually this E3 plus E3, that is much greater than this pairing energy. So that's why even if we subtract this pairing energy, this value is still higher than this E3 value. So this E3 plus E3 minus 3p, this value is much higher than this E3 value. So that's why this full field configuration is much more stable compared to the half field configuration. Okay, got it? Now let's see the trend of ionization energy along period. So this one is for S and P block elements. So if we go along period, we see that principal quantum number is sorry, this one is along group. So we are going along group. We have already discussed about along period. Sorry. So if we go along group for S and P block element, we see the principal quantum number is increasing. That means the number of shell or number of orbit is increasing, right? From beryllium to magnesium to calcium, the number of orbit is increasing. So the size of the atom also increases. So I will try to draw again. If this is the attractive girl and these are the orbitals where these lower electrons are roaming, So the principal quantum number is increasing as we go from top to down of the group. The size of the atom also increasing because we are putting more and more orbits. Now Z star, effective nuclear charge, is also increasing, which works in the opposite direction. Now we can neglect this contribution. Just to let you know, I am giving this information, but this red ones, whatever I have written in red, so those factors are minor factors. So the increase of Z star or effective nuclear charge is minor in this case, and the increase of radius is predominant. So as the radius is increasing, as these electrons are going far away from this nucleus, so it will be easier to remove those electrons. For example, if we need some energy to remove this electron, if we have another orbit, it will be much easier to remove these electrons because this electron is further from the nucleus and this electron is closer to the nucleus, right? So this electron has lesser attraction to the nucleus. That's why it will be easy to remove this electron. So hence, as we go from top to down of a group, the ionization energy decreases. So that was the case in case of S and P block elements. Now let's see in case of D block elements. So in case of D block elements, when we go along the group from top to bottom, the high effective nuclear charge due to D and F contraction. So the effective nuclear charge increases because of the D and F contraction. So the D and F electrons, they are actually diffused in nature. They have less shielding power. So that's why the further S and P electrons, those are having more attraction towards the nucleus. So the effective nuclear charge is much more to those electrons, furthermost electrons also. And also the penetrating power is the s orbital is having the more penetrating power compared to p, compared to d, and compared to f, right? So s orbital is having the highest penetrating power. So ns orbital penetrates n-1d and n-2f orbital. Hence, to remove electron from ns orbital, much more energy is needed. Now let's try to understand what is this penetrating means. So I will just give you a crude idea. Now let's see. So we have different orbitals. Just think we have some more energy levels here. Now when we consider this electron, let's put one more orbital here. And let's consider that these are the d electrons we have here. Okay. If we have d electrons here, so these d electrons are actually diffused and they'd have lesser shielding power. So this attractive girl nucleus will attract this electron or this lover, right? So this lover will try to come close and actually it will go close and it will go beyond this n-1d or n-2f. It will go closer than these d electrons and f electrons. So that's why this this contraction is also known as penetrating power. This s orbital can actually penetrate this d orbital and f orbitals, whatever present there, and it can go inside. Again, try to understand, when we have more number of d and f electrons, their shielding power is less, and that's why this nuclear's attraction is more in this ns electrons. So these ns electrons will feel more attraction towards this girl, and that will go inside, penetrating the d and f electrons. Clear? So as the effective nuclear charge increasing, as well as the penetrating power of S is much more. Hence, the ionization energy increases. So we have seen for S and P block elements along group, the ionization energy is decreasing. But in case of D block elements along the group, if we go from top to bottom, the ionization energy is increasing. So this is not exception. This is actually rule for these D block elements. If you go from top to bottom, the ionization energy will increase. Now let's see some comparison to make it clear. Okay. Now if we take this group 1 elements, lithium, sodium, potassium, rubidium and cesium, and we see the first ionization energy, so we can see it is decreasing. As we go top to down, it is decreasing, or we can say from down to top, it is increasing this way, right? In case of lithium, it was having 520 kilojoule per mole, whereas in case of cesium, it is coming down to 375 kilojoule per mole. Same thing we can see in this group, group 14, carbon, silicon, germanium, tin and lead. Again, we can see the ionization energy is actually decreasing from top to bottom, or we can say from bottom to top, it is increasing. In case of carbon, the ionization energy was 1086 kilojoule per mole, whereas in case of lead, it is only 715 kilojoule per mole. But now let's see the D block elements. So in case of D block elements, if we see group 4, titanium, zirconium and hafnium, we see as we go down the group, the ionization energy is actually increasing. In case of titanium, it was 658 kilojoule per mole, whereas in case of hafnium, it is 760 kilojoule per mole. Again, see group 5, vanadium, niobium and tantalum. So you see, in case of vanadium, the ionization energy was 650 kilojoule per mole, whereas in case of tantalum, the ionization energy is 761 kilojoule per mole. So in case of S and P block elements, as we go down the group, the ionization energy decreases. In case of S and P block elements, whereas in case of D block elements, as we go down the group, the ionization energy increases. So I hope this is clear. So this is not any exceptional case. This is actually rule for the D block elements. Okay. Now these are some conversion factors that you need to remember to calculate any, to do any example or sum. For that purpose, I have noted down these conversion factors. So 1 EV per atom is equal to 96.5 kilojoule per mole, and 1 EV per atom is equals to 23.06 kilocalorie per mole. Now, how to convert this? You can convert this EV. This EV is actually charge into voltage, right? And the charge of electron we know 1.6 into 10 to the minus 19 coulomb. And if you consider that 1 volt, so we get joule per atom. So coulomb multiplied by volt is joule per atom. So we get 1.6 into 10 to the minus 19 joule per atom. Now this is per atom. So if you want to convert it per mole, you have to multiply it by Avogadro number. So if you multiply it by 6.022 into 10 to the power 23, you will get the value of EV in joule per mole. Now from this joule per mole, you can convert to it in the kilojoule per mole and you will get this value. 1 EV per atom equals to 96.5 kilojoule per mole. Now this is the chart which I thought to show you. This chart shows first, second, third, fourth and fifth and sixth ionization energy of these elements or atoms. For case of in the case of hydrogen and helium, you can see hydrogen has only first ionization energy. That is obvious because it has only one electron, right? So it cannot give more electrons, right? In case of helium, it has first ionization energy and second ionization energy. That is also obvious because helium has only two electrons. So at max we can take out two electrons. Similarly, lithium has three ionization energies, IE1, IE2, IE3. Beryllium has four, boron has five, and rest of the elements can have more ionization energies. We can take out more and more electrons, but yeah, at the cost of higher and higher energy. If you see in case of carbon, first ionization energy is 1086 kilojoule per mole, whereas second one 2350, third one is 4620, fourth one is 6220, and if you see the fifth and sixth, that is way high. You can see this one is 38,000 and this one is around 47,000 kilojoule per mole, because as you remove more and more electrons, that will the element will become positively charged ion, and those ions will have much more z effective or effective nuclear charge. They will have much more attraction towards the nucleus, so it will be much more difficult to remove more and more electrons from the ions. So you can note down these values if you need. And this periodic table shows the first ionization energy of these elements in EV per atom unit. Now we will briefly discuss about the ionization energy of molecules. So earlier till now we have seen the ionization energy of atoms. Now we are going to consider the ionization energy of molecules. So with the increase of electronegativity of the central atom, the ionization energy of molecules increases. For example, if we see the trend in the binary hydrides, so we can see here we have nitrogen as a central atom, then oxygen, and then fluorine. So as the central atom is becoming more and more electronegative, what is the electronegativity that I will show in the later part of this slide or of this lecture. I'll describe this electron affinity and electron negativity, all these things. Just for the time being, just remember, as we are increasing the electronegativity of this atom, the ionization energy increases because the central atom holds the electrons, bonded electrons, more tightly. Similarly, in the case of pH3, phosphorus is the central atom. Here, sulfur is the central atom. Here, chlorine you can consider as the central atom. And as we increase the electronegativity, the ionization energy of the molecule increases. Same trend you can see in case of these halo acids, fluorine, chlorine, bromine, and iodine. As fluorine is having, um, fluorine is the most electronegative element, so it is having higher ionization energy. The HF is having higher ionization energy. So it means in case of HF, if you see this, this is the HF, and in case of HI, if you see HI, so if you want to take out these bonded electrons from HF or HI, the ionization energy will be much higher in case of HF. So it will be much more difficult to remove the electron from this HF molecule. Now similarly you can see these other examples. NF3 will be having higher ionization energy compared to NH3, and PF3 will having higher ionization energy compared to PH3. Yeah, this one I have to explain. See, NF3 is having higher ionization energy compared to NH3, but PF3 is also having higher compared to PH3, but the amount is not very significantly high as expected. Okay, so the ionization energy of NF3 is higher than NH3 by 268 kilojoule per mole, but the ionization of PF3 is higher than PH3 by only 121 kilojoule per mole. So this can be rationalized by considering the 2p to 3d back bonding, p pi d pi back bonding. Now, in case of NF3, so this there is no vacant orbital in case of nitrogen. So that's why these fluorines are just pulling the electrons, right? Fluorines are pulling the electrons towards itself. Now, in case of PF3, so phosphorus is having vacant 3d orbital. So that's why these electrons of the fluorine, it can actually go to the vacant 3d orbital of the phosphorus, and that can make a double bond. You can see here is a double bond. F plus means fluorine has given its electron to the phosphorus, and all these fluorines time to time can give their electrons to the phosphorus. So this is called p pi d pi back bonding. So fluorine is giving back electrons to the phosphorus. Now because of this reason, you can see there is a potential negative charge in case of phosphorus. So as it is a negatively charged, you can relatively easily take the electron out. Okay. In case of NF3, fluorines were actually holding these electrons. They were dragging these electrons. So as when you are trying to remove electrons from NS3, you have to put higher ionization energy. You have to give more energy. But now in case of PF3, fluorines, yeah, they are pulling the electrons because of the inductive effect. But at the same time, because of the resonance effect or p pi d pi back bonding, they are also giving back the electrons. Now this phosphorus or the central atom is having partially negative charge. This is called a delta negative charge. Delta sign is like this. So because of this partially negative charge, relatively easier it is to remove that electrons, to remove the electrons from PF3. Okay, but yeah, still the ionization energy of PF3 is higher than PH3, because in case of PF3 these fluorines are having inductive effect. They will hold the electrons tightly compared to PH3, right? So there will be lesser, if you see this, I'll do here PF3, and here I will make PH3. So just try to understand ionization energy of these molecules. Although hydrogen is more electronegative compared to phosphorus, but still you can think there is significant amount of electron density on this phosphorus. Now when you have fluorine, that fluorine actually drags this electron cloud towards itself more compared to the hydrogen, right? That fluorines are dragging the electrons. So now the electron density over this phosphorus will be less. It will be there, but it will be less. But it cannot completely reduce this electron density, right? Because fluorine is doing p pi d pi back bonding also. That's why it is also giving it back. Some electron density will come back. So comparatively, we have lesser electron density on this phosphorus. So as the electron density is lesser, so this phosphorus will hold these electrons tightly, right? That's why you have to give some ionization energy to take out those electrons. Now that ionization energy will be higher compared to this pH3. Okay. As it is having lesser electron density, it will hold the electrons much more tightly. And because that, if you want to remove electron from PF3 molecules, that ionization energy will be higher, 121 kilojoule per mole higher compared to the ionization energy of this pH3, right? So note out that PF3 will have higher ionization energy compared to pH3. This one is clear. Let's try to understand it again. This one is pH3. Hydrogens are pulling the electron a little bit, but still there is significant amount of electron density in the phosphorus. Now when we have PF3, fluorines are pulling those electron cloud towards itself. Now phosphorus is having less electron density. Now when it has lesser electron density, then this phosphorus will have much more attraction towards its electron cloud, right? So it will tightly hold those electrons. That's why you have to put more energy to take out electron from this PF3. But in the other case, these fluorines, they are actually giving the electron back by p pi d pi back bonding. 2p, from 2p of fluorine to 3d of phosphorus. So now because of this p pi d pi back bonding, some electron density is going from fluorine to phosphorus, and that is actually little bit increasing the phosphorus's electron density. So that's why the ionization energy, which could be much more, that is not very mm, mm, bigger number compared to the pH3. Okay, for example, if I give some arbitrary numbers, just take for example this pH3's ionization energy is 100 unit. Okay, 100 unit. Now in case of PF3, if we consider that this PF3, uh, these fluorines do not involve in the back bonding. Okay, if the fluorines do not involve in the back bonding, that time the ionization energy should be around 500. Just arbitrary numbers. Okay, now as the fluorines are giving back the electron density, so the phosphorus is gaining some electron density, so it is somewhat easier to take out the electrons. So now the ionization energy comes down around 300 or 250, you can say. So actually if there was no p pi d pi back bonding, the ionization energy would have been much bigger value. Okay, but as there is p pi d pi back bonding, the ionization energy is relatively small, but still it is large enough and larger than the ionization energy of pH3. Fine, is it clear? If you still have any confusion, please go back 5 to 10 minutes and then see the video again. And still, if you are not able to understand, you can comment down below. I will make a separate video on this. So what are the key factors or keynotes regarding this ionization energy? So we have observed that ionization energy is upright property. I will take the laser pointer. So ionization energy is upright property. And do not get confused with the term ionization potential. Okay, so ionization potential is an intensive property measured by volt, whereas ionization energy is an extensive property measured by EV per atom or kilojoule per mole. So ionization energy is slightly different than the ionization potential. Inert gases having highest ionization energy along period occupy the peak positions in the graph, and alkali metals are having lowest ionization energy along a period. From left to right along a period, ionization energy increases for S and P block elements, whereas for D and F block elements, the variation is very less. So there is very slight increase. And if you see from top to bottom along a period, ionization energy decreases for S and P block elements, whereas from top to bottom along a period in D and F block elements, ionization energy increases. So this is due to the less shielding effect of D and F electrons, known as D or F contraction or Scandide and lanthanide contraction, and higher penetrating power of S orbitals, which I have already explained these things. So this increase in ionization energy along period is not an exception, rather a rule for T block elements. Okay, so these many things you have to remember for the periodic trend in ionization energy. So next we are going to discuss about the periodic trend of electron affinity. So this one is also a upright property. That means the electron affinity increases in the upside from bottom to top in the group and from left to right along the period. So first let's try to understand what is the meaning of electron affinity. For that we will take example of this. So let's suppose this guy. So this guy likes this woman. Now he is thinking of proposing this woman. So he went with a bouquet of flower and he proposed. Now it's up to this woman that whether she will accept this flower or not. If the woman like him back, then she will accept it. She will say yes. But if she doesn't like him, then she will say no. So it's actually the decision of the woman, right? Similar thing happens in the atomic world, that when you are trying to put an extra electron to an atom, so that time the atom, the atom is accepting that maybe that atom is accepting that electron, or it may be reluctant to take that electron, right? That's why let's take the definition. Let's see the definition now. So electron affinity is the amount of energy released when an electron is added to the valence shell of the isolated gaseous species. It may be atom, ion, or molecule. So you are trying to add an extra electron in the valence shell of the isolated gaseous species. Now, if the atom is willing to take that electron, then the energy will be released. And if the atom is reluctant to take that electron, then you have to give some energy. You have to put some energy. So this one was the older definition, and recently it has been changed, and it is said that energy required to detach an electron from the singly charged negative ion. So the energy for the process of x plus E is equal to x minus. So the same thing, as you are adding an electron to the atom, or you are detaching an electron from the singly charged negative ion. So already you have added the electron to the atom, and now you are detaching that extra electron. So it is just two different ways to look at the same incident. Is it clear? So you are trying to put an extra electron in the atom. Now, depending upon the atom's electronic configuration, it might take the electron, and then if it easily takes, it will release the energy. And if it doesn't want to take the electron, then you have to provide extra energy. Now let's take some examples. So some atoms readily attract electrons, and the electron affinity has a negative value, meaning that energy is released, as I was talking. So in this case, the girl said yes to that person because the girls like him back. So that's why you can see, if you put an extra electron to the chlorine, the delta H of this process is negative. So it is exothermic, minus 349 kilojoule per mole. So the chlorine atom easily takes electron. Most atoms, however, do not accept additional electron readily, and the electron affinity is a positive value, indicating that energy must be used to add the electrons. For example, nitrogen. So we have already seen that nitrogen has half-filled configuration. So if you want to put one electron, it is not energetically favorable. So the nitrogen atom will not try to take this electron. So if you have to force it, you have to put extra energy to make it N minus. So that's why the enthalpy of the process is positive, plus 20.3 kilojoule per mole. Now things to remember, that positive value of electron affinity indicates endothermic process, which is not favorable. That means you have to invest energy, you have to put more energy. And negative value of electron affinity indicates exothermic process, which is favorable, readily acceptable. Means chlorine is readily taking the electron. Similarly, fluorine is readily taking the electron. So if the electron affinity is negative, the process is favorable. Now let's see the periodic trend of this electron affinity. So as we go from left to right along a period, the electron affinity increases. And as we go from top to bottom along a group, the electron affinity decreases. So what we can say, along group, if we go bottom to up, the electron affinity increases. So it is increasing from left to right and bottom to up. So actually it is increasing in this diagonal way. That's why I call it upright property or UR property. Now let's see the 3D plot, 3D bar plot for this electron affinity values. You can see as we come from left to right, the electron affinity increases. And as we go from top to down, the electron affinity decreases, right? So what are the reasons behind it? So we will try to understand. For this, I will take this pen. So principal quantum number is fixed along period when we go lithium, beryllium, boron, carbon. So that time the principal quantum number is fixed or the number of orbit is fixed. Shell number is fixed. Effective nuclear charge increases. So we have already seen that as we go from left to right, the effective nuclear charge increases and size gradually decreases. So same thing we have already seen during the atomic radius, periodic trend of atomic radius, atomic volume, all these things. So as we go from left to right, so we put more and more protons, means the girl is more and more attractive. So that's why these boys, these electrons which are in the outermost shell, they feel more and more attraction towards this girl. So that's why they shrink, right? The size is also decreasing and the effective nuclear charge is also increasing because we have more number of protons in the nucleus. Now when we put more and more electrons, when we go from left to right, so electron repulsion also increases, but you can ignore this fact. That's why I have marked it in red. This contribution is very minor and the other contribution uh, that decides what will be the effect. Okay, so this point is just for your understanding and learning. You can ignore this point for considering the electron affinity trend. So thus the electrostatic attraction of nucleus towards incoming electron increases along the period and electron affinity increases. That means when we are trying to put another electron from here to this valence shell, so as we are going left to right along a period, we can see this electrostatic interaction of nucleus to this valence shell's electrons are increasing. So if we put one more electron, it will easily come and the nucleus will attract it with more electrostatic interaction, right? So that's why it will be a favorable process. So as we increase the number of protons, the electrostatic attraction increases and electron affinity also increases. If we place another additional electron, that will easily come and sit in the valence shell. So that's why along a period, the electron affinity increases. You can see here from the graph, here you can see lithium, beryllium, boron, carbon, those things we will discuss. Now let's see along the group. What is the trend along group? So along group, what are the factors are there? Size of the atom increases. So as we go from top to bottom, we have more and more shells or orbits. So that's why the size of the atom increases. Now effective nuclear charge slightly increases, which acts in the opposite direction. But this point is minor, so we can neglect this point. So this is written in the red. This is a minor factor. Now incoming electrons are placed in a higher energy level far from the nucleus. Let's try to understand what it is written here. So when we have let's suppose an element which has only two shells. And when we go from top to bottom, let's suppose we have another atom which has, so I am drawing it half circle. This will be actually full circle, okay? My full circles are not good. That's why I'm just drawing half circle. Oh, my half circles are also not good. Anyway, so try to understand. When we have this element which has only two shells, as we go along the group and we have another next atom which has three shells, next atom which has four shells. So when we are trying to place an external electron, we are actually placing the electron here in the second shell, right? But in case of this, when we are trying to place an additional electron, we are placing the electron in the fourth shell. So this nucleus is much more closer in this case. The nucleus to the incoming electron distance is lesser in this case, whereas in the right hand side, the nucleus to this distance is much more. So as the distance increases, the electrostatic attraction decreases. So here the distance is less, so the attraction is more. So you can in terms of girl, you can figure out that if the boy is close to the girl, if they meet regularly or they are very nearby, they live nearby, then there is a high chance that there will be more attraction. But if the girl is very far away and the boy is in another city, so in that case it will be difficult. The attraction will be less, right? They will meet very less. It will not be frequent. So the incoming electrons are placed in a higher energy level far from the nucleus. In case of these elements where we have more and more shells. Thus the electrostatic attraction of the nucleus towards incoming electron decreases along the group, and electron affinity also decreases. So as we go from top to down to the group, the electron affinity decreases. You can see from here, fluorine is here, then bromine is less, iodine is much more less. So electron affinity decreases along the group. But there are some exceptions. So 3p elements, they actually have higher electron affinity compared to 2p elements. But according to the periodic law or periodic trend, actually it should be the opposite. You see here, the electron affinity is actually decreasing, right? From top to bottom of the group. So this fluorine, when we are going fluorine to chlorine, the chlorine's electronegativity should be lesser according to this periodic trend. But actually, this chlorine's electronegativity is more than fluorine. Or in the other language, we can say 3p elements have higher electron affinity compared to 2p elements. Now let's see the pairs. So we have fluorine and chlorine, and this is the electron affinity value. So chlorine has higher electron affinity, and in the pair of oxygen and sulfur, sulfur has higher electron affinity. In the pair of nitrogen and phosphorus, phosphorus has higher electron affinity, and in the pair of boron and aluminium, aluminium has higher electron affinity. But the electronegativity trend is actually completely opposite. Now why so? What is the reason behind it? So to understand that, we have to consider these 3 points. So first one is 2p atoms have smaller size and greater electrostatic attraction. So the 2p atoms, they have smaller size. So smaller size means greater electrostatic attraction towards the incoming electron. But the extra added electron creates electron-electron repulsion. So although it has higher electrostatic attraction, that's why the electronegativity is more in case of 2p elements, But the extra added electron, if we add one extra electron, that creates electron-electron repulsion in that valence shell. Now the repulsion is large in second period elements, but the repulsive force is not so large in the third period element. Now in the third period element, in the 3p, 3p has bigger size compared to 2p, right? So when we are adding electron in the 2p, that time electron-electron repulsion is very high. But if we are adding electron in the 3p, that time it can manage, it is not that much high. The next point is possibility of delocalization of increased electron density in vacant 3d orbital reduces the repulsion for third period elements. Now in case of third period elements, they have a vacant 3d orbital. So the incoming electron, which is increasing the electron density, so the atom can pass that electron density to the vacant 3d orbital. And in that way, it can reduce the electron-electron repulsion, right? So that's why these 3p elements, they have higher electron affinity, whereas 2p elements, they have higher electron negativity. What is electron negativity? We are going to learn after this electron affinity. Okay, so just remember these 3p elements, they have higher electron affinity because the electron-electron repulsion is less, because the electron can be delocalized in the vacant 3d orbital. And these 2p elements, they have lower electron affinity compared to the 3p because of the increased electron-electron repulsion. Okay. Now we will see in case of d block elements. So sometimes electron affinity do not show apparent trend. For example, electron affinity of manganese, which is half filled, and zinc, which is full filled, is 0. So this is the electron affinity data for d block elements. Now if you see, so we said along the period, if we go from left to right, the electron affinity increases, right? So from here to here, the electron affinity actually should increase. And we can see in the case of titanium, vanadium and chromium, the electron affinity is indeed increasing. But in case of this manganese, the electron affinity comes to 0. And from here to here, again the electron affinity is increasing. But again in case of zinc, the electron affinity is 0. Now this happens because in case of manganese, I will show you the 3D cell. So in case of manganese, the 3D is actually half filled. So in case of manganese, it is 3d5. One electron here, another electron here, another electron here, here, and here. So I have already taught you that when it is in half filled situation, that time the exchange energy is very high. Exchange energy contributes in the stability of the system or stability of the atom, right? So in case of manganese, it is 3d5 configuration, electronic configuration. So these 5 electrons are having much high exchange energy. So that's why it is very stable structure. And this manganese element or atom, they don't want additional electron. If the additional electron comes, it will come and sit here and it will do the pairing. So this manganese do not want that. That's why this half filled configuration is having 0 electron affinity. Similarly, in the case of zinc, zinc is actually 3d10. So there are 5 more electrons here, 7, 8, 9, and 10. Here also you see we have these 5 electrons of same spin, and we have these 5 electrons of same spin having down spin. So now these 5 electrons can be stabilized due to the exchange energy, okay, due to exchange of their position. they can give extra stability to this atom. So that's why zinc also do not want to get additional electron. So that's why the electron affinity is 0. Now the next factor is because of lanthanide contraction, the post lanthanides show unusually high electron affinities. Now lanthanide contraction I have already explained in the lecture 5. So as these F electrons have less shielding effect, so the atom size actually contracts, it shrinks. So because of that, the atom size is very small and the nucleus to valential distance, the radius r or atomic radius, that is very less. So that's why the nucleus is having higher electrostatic interaction to the incoming electrons, right? I will simply draw it for you. So this is the nucleus and there are multiple shells. Now consider this, that there are F electrons here in this layer. Okay, just consider F electrons are here. Now F electron has very less shielding power. So what, and it is diffuse in nature, less shielding power. So what happens, the next orbit, which is after this F, whatever will be the next orbit, so that electrons, they experience high attraction force towards this nucleus. So this orbit actually shrinks, it comes closer and it comes here. So as it is shrinking, you can see the distance is decreasing between the nucleus and this valence shell where is the electron density is maximum. So this distance, which is denoted as r, this distance is decreasing now. So this nucleus can now have higher electrostatic interaction. So if you want to place another additional electron, if this F electrons were not there, you had to place it here. But now as you have F electrons, D electrons, because their shielding effect is less, this orbit has shrinked here. Now you are placing this electron actually here. So much closer to the nucleus. So that's why they have unusually high electron affinities. These post lanthanides have unusually high electron affinities. For example, gold has a very high electron affinity, which is 223 kilojoule per mole. So among the metals, gold has the highest electron affinity. Now for your reference, you can check this data. Here I have mentioned the electron affinities. You can see the electron affinity values here. Now you can see greater than 0 means it doesn't want to take electron. These are having a full-filled shell. That's why the electron affinity is greater than 0. They don't want to take electrons. Similarly, nitrogen also greater than 0. And especially these inert gases also. They have also full-filled shell. They also don't want to take electrons. And the electron affinity is greater than 0. Whereas if you see this fluorine, chlorine, bromine, iodine, they have negative, very high negative electron affinity. So they readily accepts that electron, the incoming electron. So let's see some key points, whatever we have learned in this lecture regarding periodic trend of electron affinity. So we found out that this is a upright property. So it increases in the from left to right. If you go along period, it will increase, and if you go bottom to up along a group, it will increase. Do not get confused with the term electron affinity with electronegativity. So electron affinity is a discrete atom's property. So electron affinity is actually an inherent property of the element or the atom. Whereas electronegativity is the property of a molecule, so bound with another atom. So one atom will have single electron affinity value, but it can have multiple electronegativity value depending on its environment, depending on its with which atom it is bound. Okay. Metals like to lose valence electrons to form cations to have a fully stable octet. They mostly don't like to take electrons. So that's why for metals, the electron affinity value is very less or maybe sometimes greater than 0. For alkali metals, NS1 electronic configuration, the accommodation occurs in NS level and gives NS2 configuration. Whereas for alkaline earth metals, they already have stable full-filled electronic configuration. Thus, the process is favored more in group 1 compared to group 2. Because that group 2 elements, they have already NS2 configuration, full-filled configuration. So they are not favorable, they do not favor, they don't want to take the additional electrons. Whereas the group 1 elements having NS1, they can take the electron and they can achieve NS2 state. Nonmetals like to gain electrons to form anions to have a fully stable octet. They release energy, that means it's an exothermic process, to gain electrons to form an anion. Thus, electron affinity of nonmetals is mostly negative. That we have already seen in case of fluorine, chlorine, bromine, right? Those are having negative electron affinity values. Elements with electronic configurations of Ns2, full-filled diamagnetic atom with no unpaired electron, Ns2np3, that is half-filled, and Ns2np6, those are the inert gases, have positive electron affinities because they are unusually stable. They are very much stable, these full-filled and half-filled configurations. So that's why they have positive electron affinities value. They don't want to take additional electrons. Okay. Next, we are going to discuss about the periodic trend of electronegativity. So this is also a upright property. That means along a period, if you go from left to right, the electronegativity value will increase, and along group, if you go from bottom to up, the electronegativity will increase. So first try to understand what is electronegativity, right? Now you guys have already seen, I guess, this rope pulling game. So there are two teams and both the teams will try to pull the rope in their side. So if this team can pull the rope in their side and these members comes this side, so this team wins the game, right? Similarly, if this team can pull the rope in their side, so this team wins. So this rope pulling game is the ideal situation that happens in a bond. So in a bond, two atoms are there, but they are continuously pulling the electrons. I will take a pen. See, assume this team is actually team A, okay, and this team is actually team B. Now in between we have a rope. Just call it a bond. Now this bond is consisted of electrons, right? Two electrons. Two electrons make a bond. So these atoms, they will try to pull those electrons towards itself. Similarly, this atom B, that will also try to pull these electrons in their side. So this is exactly how we play this rope pulling game. So this atom is also pulling these electrons in their side. This atom also wants to pull the electrons in their side. Now, whoever will be the stronger, if let's suppose B is stronger, so if B can pull these electrons in their side, so we will say the electronegativity of B is higher or greater than the electronegativity of A. Okay. Let's see the definition now. So it is defined as the electron pulling capacity, that electrons in a bond of an atom towards its nucleus in a covalently bonded molecule. So this AB, which has a covalent bond in between them, they are trying to pull the electrons, and the electron pulling capacity is defined as the electronegativity. Now key points. So there should be a covalent bond to define the electronegativity of any atom, and electronegativity is not an inherent property, so it depends on its surroundings. So if you change the atom B to atom C or atom D or any other atom, the electronegativity of all the atoms will change. Okay. Now this periodic table shows the electronegativity value of the elements, periodic element of all the atoms. Now from this data we can see, if we go from left to right, let's take this lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. If we go from left to right, the electronegativity value increases. Again, you see in this group wise, if we go from top to down, the electronegativity value decreases. So if we go from down to top, the electronegativity value will increase. So these are the electronegativity values of all the atoms. And this is the 3D bar plot from which you can clearly see that electronegativity is increasing along the period, and if you see here, it is decreasing along the group. Now let's see the reasons. What are the reasons behind it? So let's first see the electronegativity trend along period. So along period, what are the factors there? Principal quantum number is fixed. So the number of shells are fixed. Effective nuclear charge increases. I have already shown multiple times that as we go from left to right, the number of proton increases. So that's why the effective nuclear charge also increases, and size gradually decreases. So we have same principal quantum number, we are filling electrons there, and the number of proton is also increasing. As the number of proton is increasing, the effective nuclear charge is increasing, and size is also gradually decreasing. And as we have more and more electrons, the electron-electron repulsion also increases, but this is a minor factor, we can ignore this. So considering all these factors, we can say that electrostatic attraction of nucleus towards bonding electron increases along the period, so the electronegativity also increases. So I will draw it here. You see, this is the nucleus of atom A. Oh, sorry. And this is the nucleus of atom B. So here the principal quantum number is fixed. So the number of shell is fixed. It will have same number of shells, but you see the size is smaller. As we go along the period, the size becomes smaller. So if you form a bond between some another atom, uh, let's suppose atom A. Now if this one is forming a bond with atom A, and this one is forming a bond with the atom A, now if the electrons are here somewhere in between the bonds, you can see the electrons of the bonds will be much closer to this nucleus compared to the electrons of these bonds. Okay, For example, if we see these electrons here and these electrons somewhere here, so these electrons are actually much closer to this nucleus because it has high effective nuclear charge and small size. So if the size is small, that time the electrostatic attraction will be more, and that will attract the bonded electrons, that will attract towards itself. So that's why the electronegativity will also increase. That you can see from this atomic number versus electronegativity plot. So as you go from lithium to fluorine, lithium, beryllium, boron, carbon, nitrogen oxide, and fluorine, you can see the electronegativity is gradually increasing, or sharply. You can see electronegativity is sharply increasing here, right? So similarly, if you go along period, as the size shrinks, the electronegativity increases. Now let's see along group. What is the effect that is playing role along group? So if we go from top to down along the group, the size of the atom increases. Now size of the atom increases means the electrons, bonding electrons, will be much uh, farther from the nucleus, right? For example, let's see this atom, and let's take another atom. Now as you are going from top to bottom, the size of the atom increases, the number of orbits also increases. Now if you make a bond between another atom A and here another atom A, so these bonded electrons are actually much further in this case, whereas these bonded electrons will be much closer to this atom. So this atom having smaller size, it has more electronegativity. Now in this case, in this atom, it is down to the this atom. So in a group we are going from top to down. So the number of orbits is increasing, number of orbits are increasing. As a result, the size of the atom is also increasing, and these bonding electrons are placed far from the nucleus. So this is the nucleus, and these bonding electrons are placed far away. So that's why the electronegativity decreases along a group. Now here is one more point, that effective nuclear charge slightly increases, which acts in the opposite direction, and it's a minor effect. Now if you see one this element, fluorine, then chlorine, then it might be the bromine. So these elements show that as you go from top to bottom along the group, the electronegativity decreases. But there are some exceptions, and the exception lies in the D series. So 3D to 4D electronegativity falls slightly, but 4D to 5D electronegativity increases due to lanthanide contraction. So along the group, the electronegativity actually should decrease, which is happening from 3D to 4D. That electronegativity is slightly decreasing, but from 4D to 5D, the electronegativity is actually increasing because of the lanthanide contraction. So for the lanthanide, because of the lanthanide contraction, what happens? The F electrons and D electrons, they are having lesser shielding power. So the nucleus, and that is attracting more to the valence electrons, and because of that the size also contracts, and as the size becomes small, now the nucleus of the atom is closer to the bonded electron, and that's why it can pull the bonded electrons bonding electrons towards itself, and because of that reason the electronegativity will be higher. Now, now we will try to remember the electronegativity order of the first 12 elements. So this is very helpful actually, and I always remember this in many competitive exams or during practicals. Many times you need to you need to remember that which element is having higher electronegativity. For example, if I draw pH3, you need to take a few seconds to realize that which one, either the phosphorus or hydrogen, which one is having higher electronegativity, which one is having plus charge and which one is having minus charge, right? Similarly, if I draw methane, CH4, it will take you some time to realize or to remember which one will be positively charged and which one will be negatively charged. Or in case of borosilicates, that is also you have to remember, or you may need few seconds to remember which atom will be positively charged, which atom will be negatively charged, and that you can decide based on the electronegativity order. So the element which is having higher electronegativity, that will form minus, negatively charged. For example, if there is a bond between oxygen and chlorine, so O will be minus and chlorine will be plus charge. Because the electronegativity of oxygen is higher, so it will take the electron and it will become O minus, whereas chlorine, which has lesser electronegativity compared to the oxygen, so that will become plus. So for that reason, it will be handy to remember the electronegativity order of first these 12 elements. And I always remember these first 12 elements. There might be some more metals in between in these places, here or somewhere here or somewhere here, somewhere here. But those metals you may not need to know those things, but these 12 elements we need to remember. Yeah, so one more thing, that there might be some more metals in between here, but for our practical purposes, for remembering these 12 elements, we need to remember. Or even if you want to remove this first word, you can remove. So electronegativity order of these 12 elements. Now how to remember? So uh, you have gone to a Xerox shop, and in the Xerox shop you have to make photocopy of some important documents, and then you saw that your friend Firoza Osman's brother is there, and he is secretly copying some photos of girls. So how you can remember? You can remember Firoza Osman's clever naughty brother is secretly copying hot pics both sides. So you went to the Xerox shop and you saw there that Firoza Osman's brother is there. He's also copying something, and he's very clever as well as naughty. And that brother is secretly copying hot pics both sides. So he's photocopying some actress models and their photos with bikinis. So you have to remember Firoza Osman's clever naughty brother is secretly copying hot pics both sides. From this Firoza, you can remember F stands for fluorine, this one. From this Osman, O stands for oxygen. From this clever, Cl, then nitrogen will come, and from the brother, bromine will come, and from this E's, I will come, iodine. Now in this, secretly this sulfur, this first S is denoting the sulfur. From the copying, carbon, and what is he copying? He is copying hot pics. So from the hot, H stands for hydrogen, P stands for phosphorus. Both B stands for boron, and in this side this Si stands for silicon. So you can remember Firoza Osman's clever naughty brother is secretly copying hot pics both sides. Or if you know the meaning of Fokla, I remember like this also. Fokla naughty brother is secretly copying hot pics both sides. So in Bengali, Fokla means someone who doesn't have teeth. So he has lost many teeth. That's why we call it Fokla. So from the Fokla, you can remember these first three atoms, fluorine, oxygen and chlorine. And then naughty brother is secretly copying hot pics both sides. That is same as of the above. So this is the easier way in which you can qualitatively remember that which atom is having higher electronegativity compared to the other atoms. So this is a qualitatively you can remember. You don't have to remember these values. So quantitatively it is not needed, but it is necessary to remember it qualitatively, that which atom will come first. Now let's talk about Pauling's electronegativity. So the electronegativity periodic table which we saw earlier, that is actually based on Pauling's electronegativity. So it originates from the concept of valence bond theory, VBT. In a covalent bond AB, the ionic forms also contribute. The contribution depends on the electronegativity difference between A and B. So these two atoms which are forming a covalent bond, so inside their covalent bond they also have some ionic nature. Now because of the covalent ionic resonance, the actual bond energy is always greater than the hypothetical 100% covalent bond. So as I mentioned, if there is a bond between two atoms A and B, so the bond is having some portion of covalent bond and some portion of ionic bond. So that is called covalent ionic resonance. So some part is coming from the covalent bond, some part is coming from the ionic contribution. So that's why, because of this ionic resonance, because of the presence of this ionic nature, the actual bond energy, which is EAB, that is always greater than the hypothetical 100% covalent bond. So this difference gives the measure of covalent ionic resonance energy. So what happens? The actual bond, which is having higher strength, if you take that and then subtract the hypothetical 100% covalent bond between A and B, the amount whatever you will get, that represents the covalent ionic resonance energy. So how you can write? You can write this covalent ionic resonance energy delta is equal to actual bond energy minus energy of the corresponding 100% covalent bond. So this delta AB represents this covalent ionic resonance energy. That is actually EAB, the actual energy, minus EAB covalent, which represents 100% covalent bond. So this EAB covalent can be written as this geometric mean. So this is the geometric mean of these two. To understand this, first we have this molecule A2 and we have this molecule B2. Okay. Now if you break these two bonds and if you break this bond and if you break this bond and then if you join this A and B, so this energy of this AB will be actually equals to this value, square root of energy of AA multiplied by energy of BB. Okay, so we can write this value in term of this energy of 100% covalent bond between AB. So if you put that, we get delta AB is equals to EAB minus under root of EAA into EBB. Now Pauling suggested this 100% ionic character in AB bond is actually proportional to the difference between their electronegativity, that is proportional to chi A minus chi B. and that is also proportional to square root of covalent ionic resonance energy, or delta AB. So from here we get that chi A minus chi B. This chi is the symbol of electronegativity. So electronegativity of atom A minus electronegativity of atom B is actually square root of delta AB. That means if we take the square root of this covalent ionic resonance energy, we get the electronegativity difference between those two atoms. Now this chi A minus chi B, whichever is greater, you can take that. If electronegativity of B is greater, you can take chi B minus chi A. Okay. So if we put the value of this delta, which is this value, we get chi A minus chi B is equals to this equation. So here delta is in EV, electron volt per molecule. So from there we observed that chi A minus chi B is proportional to under root covalent ionic resonance energy of delta AB. Okay. So chi A minus chi B is equal to under root delta AB. And here delta was in EV per molecule. Now 1 EV per molecule is equals to 96.5 kilojoule per mole. So we can convert this value from EV per molecule to kilojoule per mole. We just divide it by 96.5 and eventually we will get 0.102 square root of delta AB. So here this delta value is in kilojoule per mole. So this delta is the covalent ionic resonance energy. And from there, if we take this value in the left hand side and we square it, then we get delta AB is equals to 96.5 into chi A minus chi B whole square. So this is the one equation that you have to remember, this one. And also this one, chi A minus chi B is equals to 0.102 square root of delta. Here delta is in kilojoule. And also you have to remember this one, here delta in EV per molecule. Simply if you just put 0.102 before this term, you will get delta in kilojoule per mole. And similarly, you can convert this EV per molecule to kilocalorie per mole using this factor. So if you just divide it by 23.06, you will get chi A minus chi B is equals to 0.208 square root of delta. So here delta is in kilocalorie per mole. So these three things, these three formulas you can remember, and from here if we just take this factor in the left hand side and then square both the sides, we will get delta AB is equals to 23.06 chi A minus chi B whole square. So these formulas you have to remember, and I will erase all these things. You can take a screenshot of this. You can pause the video and take a screenshot. Now we will discuss about different type of electronegativity. Earlier we observed Pauling's electronegativity. Now we will discuss about Mulliken's orbital electronegativity, which is represented as chi m. Now Mulliken said that electronegativity of an atom is orbital dependent, and electronegativity of an atom is related to both ionization energy and electron affinity. So Mulliken suggested that chi m of atom A is equals to half of the summation of IEA, means ionization energy of A, and electron affinity of A. So this is in EV per atom. So you can again convert this EV per atom to kilojoule per mole. You have to just uh, divide it by the factor 96.5 and you will get chi m, or the Mulliken's orbital electronegativity, is equals to 0.0052 IE ionization energy of A plus electron affinity of A. So here this ionization energy and electron affinity, those are in kilojoule per mole. Similarly, you can convert this formula in kilocalorie per mole by dividing by this factor 23.06. If you divide it, you will get chi m is equals to 0.0217 ionization energy of A plus electron affinity of A. So here ionization energy and electron affinity, they are in kilocalorie per mole unit. Again, I will remove all those inks. You can pause the video and take a screenshot. Now let's see the relation between Pauling's electronegativity and Mulliken's electronegativity. So the relation is given as chi p, means the Pauling's electronegativity is equals to 0.168 times of this ionization energy plus electron affinity of the atom and minus 1.23. So if we subtract this 1.23 from this ionization energy and electron affinity value, and then if we multiply it with 0.168, we get Pauling's electronegativity. Now this can be converted into Mulliken's electronegativity. This IE plus EA, and we know half of IE plus EA is equals to chi m. So you can just convert it to chi m, and ultimately you will get 0.336 chi m minus 0.616, which will give 0.336 chi m minus 0.2. So this is the relation between Pauling's electronegativity and Mulliken's electronegativity. And even some scientists proposed that chi p and chi m should be related like this. Chi p is equals to 1.35 times of square root of chi m, and then you subtract the value 1.37. So any of the values, both the formulas you can use to relate the Pauling's electronegativity with Mulliken's electronegativity. Now let's see some other important facts. So electronegativity is also orbital dependent, and the sequence for the normal orbitals is actually ns greater than np greater than nd greater than nf. So ns is having, so s orbital is having more electronegativity compared to the other orbitals. That because this s orbital lies closer to the nucleus. Now let's see the sequence for sp hybridized orbitals. So for the hybridized orbitals, the sp orbital is having higher electronegativity compared to sp2 and compared to sp3. Now let's see some examples. For example, if you consider carbon atom, so in case of only p orbital, the electronegativity value is 1.74, whereas when it is sp3 hybridized, the value is 2.52. When it is sp2 hybridized, it is 2.8, and when it is sp hybridized, the value goes to 3.34. So as we can see, as the s character increases, the electronegativity also increases. So if we see here, s character is 0, here it is 25%, here it is 33%, and here s character is 50%. So as the s character increases, the electronegativity of the element or atom also increases. Similarly, in the case of nitrogen, we can see in the pure p orbital, the electronegativity value is 2.52, whereas in the sp3 hybridized form, the electronegativity value is 3.74. In the sp2 hybridized form, it is 4.18, and in sp hybridized form, it is 5.14. So along with that, some additional information that we know Mulliken's electronegativity is defined as chi m, and chi m is equals to 0.5 multiplied by ionization energy of the atom and electron plus electron affinity of the atom. Now if you just change this plus to the minus sign, so that will give the absolute hardness of atom. So that gives absolute hardness, and it is represented as uh, this symbol eta. So eta absolute is given as 0.5 multiplied by ionization energy of A minus electron affinity of A. Now let's see some keynotes regarding the electronegativity. So we have observed that electronegativity is actually upright property. That means if you go along period, it increases from the left to right, and if you go along group, it increases from the bottom to top. So that's why it is upright property. Okay, and do not get confused with the term electron affinity. So electron affinity I have already discussed before. So electron affinity is hugely different than electronegativity. Okay, so electron affinity is inherent property of an atom, and it is independent of the surroundings, whereas electronegativity is the property of a molecule bound with another atom and not an inherent property. So let's take an atom A. Okay, so if you make a bond between A and B and make another bond between A and C and another bond between A and D, so in all those cases the electronegativity of A will be different. Okay, because its environment is different. It is bounding, it is making a bond with different atoms. Okay, and in Mulliken's electronegativity we take the first ionization energy and first electron affinity values. The electronegativity is also orbital and hybridization dependent, that we have just seen in the earlier slide. And electronegativity depends on the charge of atom as well. So with the increase of positive charge, the electronegativity increases, whereas it decreases with the increase of negative charge. So this happens because if you increase the positive charge, so the atom will be more and more positive. That means in the atom it has less number of electrons and it has more number of protons. When it has more number of protons, the electrostatic attraction will be more. So size of the atom will become less. Now when the size of the atom is less, the nucleus will become more powerful, and that will draw the bonding electrons towards itself. So it will try to pull the bonding electrons more and more. So that's why the electronegativity decreases when we increase the positive charge. Whereas when we decrease the positive charge or increase the negative charge, so that time we are increasing, when we are increasing the negative charge, so that time the atom is getting bigger in size. So as the atom is getting bigger and bigger in size, so the distance of bonding electrons to the nucleus is increasing. So that's why the electronegativity value is also decreasing. Okay, now let's see the periodic trend of metallic character. So metallic character is a down left property. I'll take the pen again. This is a down left property. So let's see the periodic table again. And in the periodic table, you see this portion. This portion is very crucial. This portion. So this portion is actually dividing this periodic table into two halves. So this right hand side, these are called non-metals. Whereas this left hand side, these atoms and elements, they are called metals. So here in this periodic table, these sky ones are metals and these green ones are metalloids and these yellow ones are non-metals. These middle elements, these elements which are separating these metals to non-metals, so they are having some property common to metals and some properties common to non-metals. So that's why these are called metalloids, which is in between metal and non-metals. So if I will just say one more thing, that metalloids, these are the metalloids: boron, silicon, germanium, arsenic, antimony, tellurium, polonium. So people remember it as a stair step. So you get one step, again here one step. So as a stair step, we need to remember it. And in this stair step, I remember it as 1 2 2 2 formula. That means when we are making the stair step, first we have one element, boron. Then in the next step, we take two elements, silicon and germanium. And in the next step, we take another two elements, arsenic and antimony. And again in the next step, we take tellurium and polonium. So these 1, 2, 2, 2, I remember for the metalloids. Now, how do we define the metallic character? So the metallic character of an atom is estimated as the ability of losing electron and gaining positive charge. So if you have one element, maybe let's take magnesium or sodium. So these elements, they will try to lose the electrons. If they are more prone in losing the electrons and gaining the positive charge, that time we will say that they have higher metallic character. Whereas if you take this this right hand side element, these elements, they do not want to lose the electrons, whereas they want to gain the electrons. And gaining electron, they will gain negative charge. So that's why these are called non-metals. Now if you see the periodic table, so the metallic character increases in the down left property. This metallic character is the down left property. So along a period, if you go from left to right, the metallic character actually decreases. In the other word, if you go from right to left along period, the metallic character increases. And from top to bottom, if you go along the group from top to bottom, the metallic character increases. Now why so? We are going to see. Now let's first see along period. What are the factors that are affecting along period? So along period, principal quantum number is fixed. That means the number of orbits are fixed. The number of shells are fixed. Effective nuclear charge increases. Yeah, we have already seen as we are putting more and more protons in the nucleus. So the effective nuclear charge, the attraction of that attractive girl towards the boys, that is increasing, right? Now size gradually decreases. This also we have already seen. And the other factor is electron-electron repulsion also increases, but this is a minor factor. We are not going to consider this in this case. So for this, the electrostatic attraction of nucleus towards valence electron increases along the period, and the possibility of losing electrons decreases. Hence the metallic character decreases. So that means when we are going from left to right, let's take this from left to right along a period. So what are the things happening? The effective nuclear charge is increasing and the size is gradually decreasing. So now as the size is decreasing, the nucleus can attract more the electrons, the valence electrons, right? So now if the nucleus is attracting more and more to the valence electrons, now it will be difficult to take out electrons. And the atom will not try to lose electrons. So if it doesn't lose electrons, then the metallic character decreases. Okay. Now next see along group. What are the factors that working along group? So if we go from top to bottom along a group, we can see the size of the atom increases. We have already seen that when we go from top to down, the number of orbit increases. As a result, the size of the atom also increases. Now I will show. Let's suppose in case of lithium, so this is the nucleus and this is the first orbit and this is the second orbit. Whereas if you take the sodium, in case of sodium, this will be the first orbit, this will be the second orbit, this will be the third orbit. Okay. So as we are going from top to bottom, the size of the atom increases and the outermost valence electrons are placed far away from the nucleus and easier to take out. So the outermost electrons are here in the second shell, right? Whereas in case of sodium, the outermost electron is in the third shell. So it is very easy because it is now the distance is more from the nucleus to electron. So as the distance is more, now it is relatively easy to take out this electron from here to outside. So if we take out this electron, means it will be easier to remove the electrons. So that's why the metallic character increases along the group. So as we go from top to down along a group, the metallic character increases. Now one more factor we will see, that as the metallic character is defined as the tendency to lose electrons. So that's why these metals, which we call metals, these metals can easily lose electrons. And by losing electrons, the number of electron becomes less and the number of proton becomes more. For example, let's take sodium. In case of sodium, so first we have 11 protons and 11 electrons. So as we remove one electron, so that time we still have 11 protons, but now we have only 10 electrons. So this forms a unipositive charge. So this is called a cation. So sodium forms a cation because it is a metal. And generally these metals tend to form cation by losing electrons. Whereas in the right hand side of the periodic table we have non-metals. They actually tend to form anions. They try to take electrons because they have higher electroaffinity and electronegativity. That's why they are tend to take the electrons, and by taking electrons the number of electrons compared to the protons get increased and it becomes negatively charged and they form anions. So let's see the keynotes in the periodic trend of metallic character. So this is a down left property. We have already discussed that this is a down left property. And from left to right along a period, metallic character decreases. As we go from left to right along a period, the metallic character will decrease. And from top to down along a group, the metallic character increases. And non-metallic character goes exactly opposite to the metallic character. So from left to right along a period, as the metallic character decreases, the non-metallic character increases. Whereas from top to down along a group, as the metallic character increases, from top to down along a group, the non-metallic character decreases. So if someone asks you about non-metallic character, you just simply have to reverse the metallic character trend. Okay. Now we will see the periodic trend of cohesive energy. So by the term cohesive energy, we are referring the periodic trend of melting point and boiling point. Okay. So this is actually a curvy property. Now let's see. So first we have to know that what is a cohesive energy, what is the term means. So you can see there are two different molecules. So the interaction between two different molecules, here blue one and the green one, that is known as adhesion or adhesive energy or adhesive force. Whereas the interaction between two similar type of molecules or atoms, that is known as cohesion. For example, uh, if uh, if you have a group of boys, okay, so if you have a group of boys, so all are boys, so that defines cohesion. And if you have mixture of boy and girl, so that tells adhesion. So cohesive energy or cohesion is related to similar type of molecules or atoms, whereas adhesion is related to different type of molecules or atoms. Okay. Now when there are more than one molecules, they experience intermolecular forces. As we put more than one atoms or one molecules, they will experience some intermolecular force. Either they will attract or they will repulse each other. Now cohesion is an attraction between molecules or atoms of the same substance. So as I said, it's a all boys class or all boys property. And adhesion is an attraction between molecules of different chemical substances. For example, as I said, if you put boys and girls together, some boys will talk to the girls, and that is actually adhesion, example of adhesion. Now let's see the definition of cohesive energy. The cohesive energy of a material refers to the energy required to separate constituent atoms or molecules apart from each other, or the amount of energy that is responsible for holding the atoms or molecules together. So here I will try to draw. Let's suppose you have an atom A. Now these atoms are bound to each other, okay? These atoms are bound to each other by these bonds. And you might think that these bonds are in all four directions, okay? Now if you want to take out one atom from this, you have to supply some amount of energy, and supplying energy you can break these bonds, this one or this one. So you have to supply energy and you have to break all these bonds, then only you can take out this one atom, right? So the energy required to separate this atom from rest of its atoms, that is known as cohesive energy. Or in the other word, you can say the energy that is responsible for holding the atoms. So these atoms, this atom is sitting here. So there is some amount of energy that is making it responsible to sit in that location. Okay. So that also in both terms you can define cohesive energy. Now this is the periodic table which is showing the periodic trend of melting point. And if you see, if you go from left to right, so first the melting point is increasing. So the circle, as big the circle, if the circle is bigger, that tells the melting point is more. And if the circle is small, that tells it the melting point is very low and small, and it easily melts. So as you can see, as we go from left to right, first the melting point increases, the circle becomes more and more big, and then as we go to extreme right, we can see the circle becomes more and more small. So first it increases, then it decreases. Okay. Now same thing you can observe from this 3D bar plot of melting point. You can see this. First it is increasing and getting maxima, and then it is decreasing. So if you follow this line, first it is increasing and then it is decreasing. Similarly, we can see the periodic table containing the information of boiling point of the elements. Now if you see the boiling point, that also refers to the same trend. As we go from left to right, first it is increasing, and then if we go more right, that time it is decreasing. The spots are become more and more small. That means the boiling point is decreasing. Again we will see the 3D plot, and same thing we can see as we are going from left to right. First the curve is increasing and then the curve is decreasing. Okay. Now why it is happening? So we have to understand the factors. What are the factors that are responsible for this type of behavior? So we will see first the trend of cohesive energy along period. Cohesive energy maximizes at group 14, then falls to the minima. So this is the group 14 elements. You can see if you go along period, for example, beryllium, boron, carbon, nitrogen. So the group 14 elements are having higher cohesive energies. And then again it is falling down. For d block elements, yeah, so this one is for the S and P orbital, sp elements. Whereas for the d block elements, it maximizes at group 5, 5 and 6, and then falls. So I will go back, I'll show you again. So see this boiling point data. From here you can see these d block elements are increasing first, cohesive energy, then decreasing, right? Similarly, if you see this S and P block elements, if you consider this SP together, then you will get to see first it is increasing and then it is decreasing. So the maxima is at group 14, means this carbon series. This carbon group, it will show maximum cohesive energy. Whereas in case of um, D, D block element, it shows maximum near group 5 and group 6, this region, somewhere this region. Now what is the reason behind this increased cohesive energy? Okay, that we have to find out. So the availability of number of unpaired electrons determines the extent of cohesive energy. With the increase of number of unpaired electrons, the larger number of bonds can be formed to bring more cohesive energy. Now if you see the electronic configuration, you will see that beryllium is actually 2s2, so completely filled. So I will write here the electronic configurations. Now this one is 2s2, 2p1, and for carbon it will be actually 2s2, 2p2, but so if you see this 2s2, 2p2 will look like this. So first we have this one 2s2 and then 2p2, one electron here, one electron here, and this p orbital is vacant. But what happens during bond formation, hybridization occurs and this S and P, these orbitals get merged. So this was before hybridization, 2s and 2p. And after hybridization, it becomes four orbitals together. And in all four orbitals, they have only one electron. So this is called sp3 hybridization. And carbon forms this sp3 hybridization. Now in sp3 hybridization, all orbitals have only one electron. So now all these four orbitals, they can participate in bonding. So this S, 2s and 2p, three orbitals of this 2p, they come together and then they make four, then sp3 hybridized orbital. These sp3 hybridized orbitals can make four bonds. So that is the maximum number. In case of boron, even if you do sp hybridization, that will form only sp2. So only three electrons can be there. And if you go to nitrogen, there is one more electron and that will be here. Even it is sp3 hybridized, that has 5 electrons in total. So one electron pair and three unpaired electrons. As nitrogen has three unpaired electrons, so nitrogen can form at max 3 bonds even after hybridization. Whereas carbon had 4 unpaired electrons, right? See, carbon has these 4 unpaired electrons. That's why carbon can form 4 bonds. So when carbon is in a carbon atoms are there all over, one carbon atom binds to 4 different carbon atoms. Similarly, all other atoms, for example, boron, that can bind to at max 3 atoms, nitrogen can bind at max 3 atoms. So this binding increases in case of this group 14 elements. Group 14 because they have 4 unpaired electrons. So if you see again, the availability of number of unpaired electrons determines the extent of cohesive energy. If the number of unpaired electrons are more, the number of bonding will be more, bonding within same type of atoms. So that's why the extent of cohesive energy will be more. You have to apply more amount of energy to take out that atom, right? Now with the increase in number of unpaired electrons, the larger number of bonds can be formed to bring more cohesive energy. That is what I just explained. Now Ns and Np can accommodate maximum 4 unpaired electrons through sp3 hybridization that I have shown here after sp3 hybridization. So this one is the hybridized orbital, sp3 hybridization. Okay, I'll write it as H, hybridized orbitals, which is attained in group 14. And for d block elements, d electrons can also participate in bonding. As d electrons can also participate in bonding, that's why that d block elements, they have more number of electrons to make this uh, bondings. Okay, so that's why the cohesive energy is also much greater. Now let's see what is the trend along group. So along group, number of available unpaired electrons remains same. So if you go from top to bottom of a group, the shell is same, valence electrons are same. So the number of available unpaired electrons are also same, right? Now for S and P elements, size of the atom increases. So for S and P block elements, if we go from top to down, the size of the atom increases. It becomes bigger because we are increasing the number of shell or orbits. The increased size reduces the number of bonds per unit area. So as the atoms become bigger and bigger, the number of bonds per unit area decreases. So if you have this, just see, if you have this carbon atom, let's suppose, so it can bind with this atom, it can bind with this atom, and it can bind with this atom, it can bind with another atom. Now see, within this much area there are so many bonds, so you can just multiply it. All these atoms are bound with 4 other elements. Now if you see silicon, or let's say tin, the atom size is bigger. Now that is bound to another bigger atom, that is bound to another bigger atom, now another bigger atom, and another bigger atom. Similarly, these atoms are also bound in all 4 direction, but here the circle is much bigger compared to this, right? So we have same number of unpaired electrons, we have same number of bonds, but the as the atom size is small, here we have more number of bonds per unit area, whereas as the atom size is bigger, here we have less number of bonds per unit area. So hence the cohesive energy decreases in S and P block elements as we go from top to bottom because the size of the atom increases. Now for D block elements, size change is significantly less due to the D and F contraction, which I have already explained in the previous lecture. So because these D and F electrons are diffused, they have less shielding power, and that's why the nucleus have more attraction towards the outermost valence electrons. So that's why the size change is significantly less. As we put more and more protons, it can attract the outermost electrons, and size is almost similar. So density of atoms increases. So the density of the atom also gets increased, and these heavier elements experience higher cohesive energy. So if you see here, as we go from top to bottom of a group in S and P block element, we can see the cohesive energy actually decreasing. For carbon, it is maximum, then silicon, germanium, tin, lead, the cohesive energy amount is decreasing. Whereas if you see in case of D block element, so in D block element, this curve is for the 3D element, 3D elements. Now if we go down, this one will be for 4D elements, and this one is for 5D elements. So this one is chromium, molybdenum, and tungsten. So this one chromium, then if you go down molybdenum, and if you go down tungsten. So along the group we are going down, but these heavy, as the atoms are becoming more heavy due to D and F contraction, the cohesive energy is increasing. So here you have to remember that cohesive energy for S and P block and D block along group runs in the opposite direction. Okay. Here you can see the atomic number versus melting point graph. This one, and on the right hand side the same graph you can see. So the scale is different, it is in Kelvin scale, and this one is degree centigrade scale. So here, from here we can see that carbon is having the highest melting point. And here in these plots I am showing you the atomic number versus boiling point data. So here boiling point is given in Kelvin scale, and these ones are the data. You can see, if you need for your reference, you can take a look of this periodic table. So let's discuss about the key points. So we have observed that this trend in cohesive energy is actually a curvy property. So first it increases, then becomes maximum at group 14 in case of S and P elements, and in group 5 or 6 in case of D block elements, and then it comes down. So the cohesive energy of a material refers to the energy required to separate constituent atoms or molecules apart from each other. The availability of number of unpaired electrons determines the extent of cohesive energy, and with the increase in number of unpaired electrons, the larger number of bonds can be formed to bring more cohesive energy. Now along period, cohesive energy maximizes at group 14, then falls to the minima. And for D block elements, it maximizes at group 5 and 6, and then it falls. Inert gases having only weaker van der Waals force acting as the intermolecular interaction have the lowest cohesive energies. And along group, cohesive energy decreases in S and P block elements if we go from top to down, whereas it increases in the case of D block elements due to D and F contraction. Okay. Now let's summarize all these trends. So whatever till now we have observed. So we have observed the trend of atomic radius, metallic character, ionization energy, electron affinity, electronegativity, atomic volume, and cohesive energy. And these are the short notations that you can remember, and it will be very easy for you to remember if you remember these short notations. So for atomic radius and metallic character, this is actually down left property. So the arrow is pointing at the down and left side. Whereas for the ionization energy, electron affinity, and electronegativity, the property or the trends are actually upright property. So the arrow will be in the upright corner. And for atomic volume, so this will be a curve which is going down and then increasing. And for cohesive energy, this will be a curve which is first going up and then decreasing. So these are the short notations that will be extremely helpful for you to remember these periodic trends. And this is the summary, and this is also, you can take a note or you can pause the video and take a screenshot of this This will also be extremely helpful, where I have specifically written what will be the trend in S and P block elements as well as D block elements. So all the exceptions are also written here. Next, we will quickly discuss about the extreme of this periodic properties, highest and lowest ones. So atomic radius, for francium, the atomic radius is highest. For helium, it is lowest. In case of atomic volume, francium has highest atomic volume and boron has the lowest atomic volume. Ionization energy, helium has the highest ionization energy, whereas cesium metal, which has the lowest ionization energy. If we consider the electron affinity, chlorine has the highest electron affinity and francium metal has the lowest electron affinity. Whereas in case of electronegativity, fluorine has the highest electronegativity and cesium has the lowest electronegativity. If we consider the metallic character, francium is having the most metallic character and fluorine is having the lowest metallic character or the highest non-metallic character. And if we see the number of isotopes, tin is having the most number of isotopes. It has almost 10 isotopes. And if we see electric quadruple moment, lutetium is having the highest electric quadruple moment. That means this atom is highly deformed. This nucleus is highly deformed. Now we will discuss about another important feature, that is the diagonal relationship. So the diagonal relationship signifies the similarities in properties of the elements of the second period with the respective diagonally opposite third period elements. So if you see the second period element lithium, beryllium, boron and carbon, and if you see the third period element sodium, magnesium, aluminum and silicon, so you will observe that the properties of lithium and magnesium, this pair is kind of similar, whereas the properties of beryllium and aluminum, that is also similar, and the properties of boron is also very close to the properties of silicon. Now why this happens? So to understand this, the thing is, most of the periodic trends that increases from left to right, that actually decreases from top to down along the group. So if a trend is there that is increasing this way, that will also decrease this way. Or if you go this way also, the trend decrease this way whereas increase this way. So that is how it is. These diagonal elements are actually having almost same properties. Now I will try to justify it by giving some arbitrary calculations. For example, let's take this uh, beryllium and aluminum or boron and silicon. Let's take this boron and silicon, okay? And let's consider this atomic radius and metallic character. So, for example, boron, let's consider the atomic radius and metallic character is denoted by X. And we know that atomic radius decreases along the period. So if we go from here to here, the atomic radius will decrease, right? So this atomic radius and metallic character I denote by X, it will decrease. Let's suppose it will decrease by 1 unit. So here in case of carbon, it will be actually X minus 1. And again, suppose in case of going down a group from boron to aluminum, this atomic radius and metallic character increases by 1 unit. So from boron to aluminum, it will come down and it will become X plus 1, because we are defining that from top to down it gets increased by 1 unit. Okay. Now if you go from aluminum to silicon, again the atomic radius and metallic character should go down or should decrease by 1 unit, because we have already defined that it will decrease by 1 unit from left to right, and it will increase by 1 unit from top to down. So if we go from aluminum to silicon, it will again decrease by 1 unit, and it will be x plus 1 minus 1. So ultimately we will find the value x. Same thing we can do from carbon to silicon, and if we go carbon to silicon, so in case of carbon, the values of atomic radius and metallic character were x minus 1, and from going top to down, we are actually increasing the value by plus 1 unit. So again it will be x minus 1 plus 1, so it will come as x. Now if we compare the values of boron and silicon, we see it comes nearly same, x, both are x. So that's why if we see the diagonal relationship, if we go diagonally in the periodic table, we find out that most of the properties are very close to each other. And yeah, this works in the lower atomic weight, low atomic number molecules. Okay, so this we have seen atomic radius and metallic character, which decreases along the period from left to right and increases along the group from top to bottom, right? Now let's just clear it, and let's see the trend of ionization energy, electron affinity, and electronegativity. Okay, so these things, what happens if we consider it as to be, if it is a y, and we consider that it increases by plus 1 unit. From left to right, it increases by plus 1 unit, and from top to down, it decreases by 1 unit. Okay. So now we will take this pair, beryllium, magnesium, aluminum, and boron. We will take this beryllium and aluminum. Okay. Now let's consider for beryllium, our electron affinity, electronegativity, and ionization energy values are y. Now when we go from beryllium to boron, so actually these values will increase by plus 1 unit. So in case of boron, it will be y plus 1. And when we go from top to down, from beryllium to magnesium, these values will be decreased by 1 unit. So it will be y minus 1. Now again, if we go from magnesium to aluminum, we are going along a period. So it should increase by plus 1 unit. So if we increase it by plus 1 unit from magnesium, that means y minus 1 plus 1, and we will get y. Similarly, if we come from boron to aluminum, in boron, these units were, these ionization energy, electron affinity, and electronegativity were as y plus 1 unit. Now if we go from top to down, we have to decrease 1 unit. Okay, so we will subtract 1 unit, and it will again come as y. So you can see beryllium is also having y unit, and aluminum is also having 1 unit. That's why there is a diagonal relationship between this beryllium and aluminum. I hope this method will be easier to understand. So this is a qualitative method. So this is not totally correct. Okay, the values will not be exactly same, but it will be somewhere closer. Now let's see. So all the periodic properties, for example, radius, electron affinity, electronegativity, ionization energy, polarizing power, remain more or less same for the diagonal elements of 2p and 3p. In the higher periods, the diagonal relationship cannot be seen due to the presence of d and f electrons. It results so because the group trend of some properties in the transition elements is of opposite nature compared to that in the representative elements. Representative elements mean S block and P block elements. Okay, but the trends along the periods remain almost the same for both D block and representative elements. So if we go to the higher elements, higher atoms, that time this diagonal relationship does not work, because what happens here, we were considering that if we go from left to right, it will increase by +1, and if we go from top to down, it will decrease by -1, right? So this is valid in case of 2p and 3p. But after that, when we have d and f electrons, that time this trend is not valid, because there are some properties in the d block elements that shows opposite trend. Okay, I have already discussed in this lecture. You can go back and check. So there are some trends that do not follow the order of representative elements, means S and P block elements. So maybe from along group from top to down, in case of S and P, it is increasing, but in case of D, it is decreasing, or the vice versa. But along the period, it remains same. So along the period, the properties are having same trend, but along the group, the properties may have different trend. So that's why this diagonal relationship is not valid in the higher elements. Now you can see some of the parameters that are given for these pairs: lithium and magnesium, beryllium and aluminum, and boron and silicon. I repeat again, the values will not be exactly same. Okay, the values will be somewhat different, but there will be similarity. It will not be exactly same. Okay, now you can pause the video and you can look it. My throat is actually hurting. It's a very long lecture and my throat is paining. I will not go into the details of these similarities in the pair of lithium and magnesium. If you are interested, you can pause the video and you can take a note, or you can read this. So these are for those who wants to learn more, so you can have these informations. Similarities in the pair of lithium and magnesium. Similarly, you can learn about the similarities in the pair of beryllium and aluminum. So if you are interested, you can pause the video and you can read this. I'm not going to discuss in detail. I might discuss these things in some other videos, in some other chapter. And here are some similarities in the pair of boron and silicon. So if you are interested, you can pause the video, you can take a screenshot, and then you can go through these data. Yeah. So there are multiple properties that are similar between these pairs, or the elements which are showing diagonal relationships: lithium magnesium, beryllium aluminum, and boron silicon. So I will conclude my lecture here, and most of the all these things, some things I have collected from net, some things I have collected from other teachers or professors lectures, and many things I have collected from this book. This book is actually written by Professor Ashim K Das from Vishwavarti University, West Bengal, India. Means when I was in Vishwavarti, I was doing my bachelor's, so that time I have also taken his classes, and his classes were very informative. We have learned a lot of things from here, and he has 7 volumes, if I am not mistaken. He has 7 different volumes, so you can check which part is containing which chapters. You can take a look at those volumes. These books are very informative. So I will stop here today. So in today's lecture, we have learned a lot of things, and we have learned all the periodic trends, their basic details, and what will be their trend, as well as I have given you some tricks and notes to remember all those trends. Okay, so I will conclude my lecture here and the series also. In the next lecture, which is the next lecture 7, that will be a very short class, and in that lecture it will be just for actually fun. I will not give any scientific explanations or scientific uh, informations. I'll just show you some fun stuff related to the periodic table. So there I will show you Guinness World Records regarding the periodic table, and I am encouraging you all also, you can also try to break this. These are breakable, so you can try and break these world records. World record can be yours. Then I will show some memes regarding periodic table. So memes are everywhere. Okay, so people have started making memes taking this periodic table also. Some of the memes I will show you, and I will show some periodic table apps which can be useful for learning. I hope all of the things are clear in this lecture, lecture 6. If you have any confusion or any doubt, you can comment down below. If I get a lot of comments, I will make a separate dedicated video to resolve all the issues or all the confusions. And if you feel somewhere I have said something wrong, or I have mistakenly given some wrong information, please correct it and comment it down. I think information should be correct, and we should not deliver any wrong information to anyone. So if you find anything is wrong, please correct me. Thank you. Thank you. See you in the next lecture.